Welcome to DIAS, everyone. And Harold is going to kick off. We can
probably introduce it. Okay. So I will focus on the IKKT model, which is sort of one of the models which one can consider as matrix theory. And I will try to explain how gravity in particular may arise from this model. And this is a sort of a non-standard approach. It's a bit different from the usual string theory story, but I think it's potentially very interesting. So I will try to explain this. And this will be mostly a qualitative talk. I will not enter into a lot of details, but on the other hand, I'll talk about a lot of things. So in order to avoid getting lost right in the beginning, well, I have to do that. Let me start with an executive summary. And that will be the following. So the basic message is the IKKT model is a very rich model. There's lots of things you can do with it. And it's also sort of almost unique, essentially, being a maximally supersymmetric matrix model. And so the question is, well, for me, the idea is, can this model be a fundamental model for physics? And I think it's one of the best candidates that we have. And sort of my long-term project is always to find a way to get real physics from this model. And I'm still quite optimistic about it. Of course, other people have different opinions, so let's discuss. There are several possible ways you can get physics from these models. I will focus on one approach which I think is the most promising, which is based on quantum geometry. And it's going to be a weakly coupled approach, essentially. So it's totally opposite from holography. It has nothing to do with it. In fact, it's got totally the opposite regime. So at least for the sake of this talk, don't try to understand what I say in terms of holography. It doesn't work. And the one essential difference is also that I will insist on having only finitely many degrees of freedom per volume. So that's absolutely essential thing. Otherwise, it will not work. So the kind of approach that I use requires to have only finitely many degrees of freedom per volume. And this will actually be the case, at least in the types of background that I will consider. And I will at least pretend to be in the weakly coupling regime so that one can do reasonable things at one loop. So the basic idea is that space-time arises from a non-trivial vacuum in this model, very much like in quantum field theory. You have some non-trivial vacuum, and then you get the physics that's whatever you see at low energies. So I will discuss some possible vacua, and then the fluctuations around that vacuum should give you the physical degrees of freedom and hopefully come as close as possible to the physics that we see. So of course, one thing is, well, what is the proper vacuum? Do we have a choice? How can we identify it? Of course, this is an extremely difficult question. I don't have a good answer. So what I'll do at the moment is try to make a good guess, basically. Try to find at least a background which have a chance to work, so which give you a lot of interesting physical behavior. And so that's what I will talk about. Of course, essentially, one needs to have a better control of that. And there is a number of people also in this room who spend a lot of effort on numerical approaches, trying to verify, try to see what the model really does at the non-theoretical level. It's very challenging. We will hear some talks about it. And so far, we cannot really reconcile it yet. But I also see no. Thank you. I also don't see an obstacle, at least in principle. Okay, so that's kind of a cautionary statement. And also the type of gravity theory that we will end up with is actually very interesting. And I will try to discuss a bit some qualitative distinctions from the gravity that you get here from GR. Of course, these are work in progress, but I think some rough ideas one can already see. And so this is different from what people usually discuss. So you will not have heard about this before, presumably, unless we talked about it. And some of it is not yet published. No. Yeah. So here's the outline of the talk. So first, I want to explain briefly the framework, which is matrix geometry. It's a general framework. I'll just go through the basic structures that we need. And I will briefly remind you of the importance of ultraviolet and infrared mixing in this context. Then I will introduce the IKKT matrix model because I'm the first speaker here, so somebody has to do it. And then I will focus about the gravity, the mechanism for gravity on such a background in the IKKT model. And I will actually not give too many details about the structure of minimal quantum spacetime. So there is one specific spacetime that we have in mind, which seems to be the best candidate, at least that we have. And Alessandro Manta later today will talk about more details about this space. So I will focus on some rough structures, and he will give you more details, which I will just skip for the moment. Okay. So of course, we all know that. The core quantum spaces starts, of course, with quantum mechanics. That's the prime example. The phase space in quantum mechanics is the first example of a quantum space, quantized phase space, given by the Heisenberg algebra. More systematically, you write it in terms of the worldwide quantum plane in any given dimensions. And so the basic functions are, of course, you have quantum cells of finite size given by the Planck constant, which has the reason why there is uncertainty, and you have finitely many degrees of freedom per unit volume in phase space, of course, not in configuration space, but in phase space for quantum mechanics. It is finite, and that is the core thing that we will use. But now we will use it for space-time, not for phase space. So nothing very new here. Of course, you need more than phase space structure. You need metric structure. There are several ways one could describe the metric here. One could use a Dirac-Laplace operator and try to talk about the spectral geometry. That's fine, but it's complicated. It's indirect. It's much more efficient approaches to extract the matrix, the geometry directly from matrix configurations, and I will explain how to do that. And this has to do with embedded branes, basically. It's a very stringy picture familiar from string theory. So what I mean by quantum geometry is something that will be defined in terms of a matrix configuration. So we'll have a bunch of matrices, and I claim they define a quantum geometry, and we will pick some nice ones, but it's actually a general story. Now, matrix configuration, you can have, of course, commuting matrices, and they will then define a lattice. So that's very natural. If they commute, they can diagonalize simultaneously. So you get back lattice field theory in some sense, but this is not what I'm going to do, and it's important. This is not what I will do. I think it's more reasonable in that model to talk about mildly non-commuting matrices. So the matrices will not be totally random. That's also very different from what people do in matrix models in different contexts. So it's very far from random matrices. What I talk about is sort of almost commuting matrices. And that's the point. And then you can make sense of something like an effective geometry, and that's the framework. And it gives you a smooth geometry with finitely many degrees of freedom per volume. And it's actually a very efficient way to encode geometry. And now people in data science are actually very open-minded, and they start to embrace this framework. It's very efficient. It works actually. But so I will focus on the physics aspect. Okay, so let me actually give you some brief definitions just to be precise in the beginning. So what is a matrix configuration? It's a set of self-adjoint matrices. That's all. And let me assume here that the Hilbert space is finite dimensional. It can, of course, be infinite dimensional. It doesn't really matter so much. Now, given a matrix configuration, I don't know which screen I should use.
Yeah, it won't be visible to people online anyway. So
yeah, so then maybe it's better to use the cursor. So, given a matrix configuration, you can always define the following Hamiltonian. So, take a matrix, subtract from it a multiple of the unit matrix with some number xa. So pick a point in RD, which is the target space. For any point in RD, you can define the displacement Hamiltonian, which is the sum of x, capital X minus little x square, which is, of course, by definition, a positive definite operator. Let me call this a displacement Hamiltonian. Given this Hamiltonian, you can find a ground state. So for each point in target space, you define a ground state x, which is at a certain eigenvalue, and let me call this quasi-coherent states. This is the best analog to coherent states that you can find, because in the example of the quantum mechanical harmonic oscillator on phase space, if you take x and b, the Heisenberg generators, then these are the well-known standard coherent states on phase space, which you can move around, but this can be done always, and it always gives you sort of optimally localized states. And another thing you can do with a matrix configuration, you can define a matrix Laplacian, which is the double commutator for the matrices acting on the space of matrices by the adjoint. So this is the matrix Laplacian, or similarly the D'Alembertian if you make the Minkowski matrix. Now these concepts, of course, they have come up in different contexts. So for me, it was a useful paper by David actually, and by Kovacik and so on. So all of this was sort of grew out of various ideas from various contexts, but I think it's a nice frame. Anyway, so starting from these quasi-coherent states. So for each point in target space you have a state. I just take the union of all these states. This is a subset in Hilbert states, if you like. And it's a U1 bundle. So you can take the quotient. And this is what I'm talking about. So the quantum space, by definition, is the quotient of the set of all coherent states divided by the phase. And that is, by construction, is a subspace of Cpn-1. So n is the dimension of the Hilbert. So this you can always do. And the point is, quite generically, this is a manifold, actually. This is a submanifold of Cpn-1. And, well, sometimes there are degeneracies and so on, but this is a fairly generic thing. Let me assume it's a real submanifold, and that's what I call a quantum manifold. And it's nice because this space inherits a lot of structure. It inherits a natural connection, which is the Berry connection. From that you get a closed 2 form, which is a closed 2 form omega, and also an induced metric that comes from the Fubini's 2D matrix. So that you get for free, and these are very useful things, and it holds a lot of structural properties of this quantum space. Another thing you get for free is an embedding map from this quantum space. By the way, so the quantum space by this concept is just an ordinary manifold of the submanifold of Cpn, and you get the map from this manifold into target space. Just sandwich your matrix configuration with this quasi-coherent states. For every point on M, you get the number point in Rd. And that sort of gives you the embedding of this manifold in target space. So that's now something like an embedded brain. Now, so this construction you can always do, and it always gives you something reasonably nice. You can encode lots of different geometries in this way. And so in nice cases, this is symplectic. It's not always symplectic. Let's assume it's symplectic. Then that's what I call a quantum space. And there are many examples of this that you know. So let me just go mention these examples. The first example is more alive quantum space. It's just quantum mechanics. We have the standard coherent states. Fuzzy sphere is another nice example. You start with the matrix configuration given by a large representation of SU2. So this is just a set of 3 matrices. You go through the machine, and you really find this manifold is precisely a sphere. It's exactly the sphere. And it works for any n. So even if you start with Pauli matrices, you get back to the sphere, then you get the block sphere. It works for any coadjoint orbit. So take a large irreducible representation of your favorite semi-simple Lie group. Compact, doesn't even have to be compact. So you get the number of matrices again. To the machine, you get the quantized, you get the coadjoint orbit back, and in fact also the quantization of this coadjoint orbit. And there is quantization maps and things like that. I will not go right down everything, but it works more generically. So it's not so the group theory is not essentially. It's just these are just nice examples. You start with any sort of reasonably compatible matrices, and you get a lot of structure. So, and I claim that this framework is generally enough to encode gravity. So you have enough flexibility in your geometry to include even dynamical gravity, and that's what I want to discuss a bit. Okay, so spacetime will be one of these manifolds, and it arises as kind of quantized brain in target space. Now, here's the standard dictionary, which you learn in quantum mechanics. I want to emphasize that there is one little detail that you should pay attention to. So the obvious thing is that the space of operators then is kind of a quantization of the space of functions on a manifold. In a given matrix, take sandwich them between the state, you get a function. In particular, the matrices X that you started with correspond to functions, coordinate functions of the brain in target space. Commutators correspond to Poisson brackets. The trace corresponds to the integral, which is a symplectic volume form. And the matrix Laplacian corresponds essentially to the matrix Laplacian of the effective matrix. So this is all generic. But one thing I want to get your attention to, this correspondence only works in the infrared. It really does not work in the ultraviolet. So you should restrict yourself to a space of functions with long wavelength, much longer than the scale of non-commutativity. And then this subspace corresponds to a subspace of the matrices, which let me call it local local operators or something like that, and then this sort of makes sense. This is a semi-classical picture. Then, if you go to a very high energy modes or very, if you go to general matrices, this correspondence really doesn't work anymore. For example, there are operators which have this structure. They are non-local, built from two coherent states at different points. Those are kind of stringy objects, and they have absolutely no classical correspondence. So those are not functions, those are strings. And that's why the framework of matrix models is a very much stringy framework. It's closer to string theory than to field theory a priori, unless you find a way to restrict yourself to the very infrared sector. So that's important to keep in mind. Okay, any questions about the framework? Anybody are familiar with it? So, okay, summary is we start with a set of matrices. You can sort of see what this describes an embedded brane in target space. You get the Laplacian or D'Alembertian, and then matrix models will allow to make this picture dynamic. Because matrix model gives us a sort of a dynamical matrix configuration in some sense. Okay, and it's a very efficient way to encode high-dimensional geometric data. I just want to point this out. Okay.
In what sense is it almost local?
Almost. You mean the matrix configuration?
Yeah.
Yeah. So there is a certain criterion which is, there's, for example, they should, if they act, so a matrix is almost local if it is, in some sense, acting on the quasi-coherent states in an almost local way. So, in some sense, so if you take matrix elements with quasi-coherent states being in very different locations, with this operator, it should vanish. So, essentially, it's this kind of a restriction. So, one can give some criterion what is an almost local operator. It's in the book or in the paper. It's a bit vague, but roughly speaking, it's almost diagonal on the quasi-coherent states, which means it's low energy, long wavelength. Okay, so that's the framework. Now, with this framework, let me remind you of an important aspect of, if you try to do quantum field theory in such a space, there is a standard issue which always comes up, which makes life difficult, and that comes from non-planar diagrams. Now, I'm completely sketchy. Let me not explain where all this comes from. So if you do that, try to do Feynman rules for fluctuations of matrices on such a non-commutative space. You find non-planar diagrams, and if you try to compute them, you get diagrams like this, for example, and their usual representation is something like that. You get oscillatory integrals in momentum space. They're very strange and obscure. Now, these things become much more transparent if you use the string modes. So if you look at this in position space, it's much more transparent, because exactly this diagram then takes this simple form, and what happens is, in the loop, you just exchange these string modes, which are now non-local. And then you get a diagram which connects the function on one point to the other, and then the effective one, the one-to effective action then contains a term which looks like that. So it's non-local with a scale. Well, it goes like 1 over x distance squared. This is completely generic. In any dimensions, whatever you do, any type of field theory, you always get this diagram. So the bottom line is that this kind of a field theory always, we find the universal long-range non-locality, which comes from ultraviolet modes running in the loops, from non-local ultraviolet modes running in the loops. And that's a disaster. It's not acceptable. And that was the end of non-commutative field theory, unless you find a way to avoid this.
What's the scale and L here?
L is the non-commutativity scale.
So it's correct to say that.
This is an ultraviolet scale, so basically it doesn't really matter, because if x minus y is longer than the scale, then you can forget this mass parameter.
Right, so it's correct to theta. So.
Yeah, exactly. It's split of theta, exactly. So the bottom line is, you have this problem unless you manage to tame these one loop effects, and the only reasonable way I know how to tame them is to go to maximally supersymmetric model, and that is the IKKT model. So that for me is the reason why the IKKT model is so interesting, because that's the only way, that's the only model where it makes sense to get a sort of almost local quantum effective action on such a quantum space. So that is the motivation, if you like. Now so what is this model? You know it. Was introduced by my son and collaborators. Almost 30 years ago, disaster. So you start with a matrix configuration. So you take 10 matrices, and then of course you take commutators, and you construct matrices with a 9+1 dimensional eta tensor, which is of course that is static, so the only information is in the matrices. You add some Majorana-Weil spinor of SO91, and then you get this maximally supersymmetric matrix model. That's also, it's a function of matrices, bosonic matrices, so a matrix configuration, and some fermionic matrices. I will ignore the fermions here, except that we will need to integrate them out, and so they will play an essential role just at the loop level, but not beyond that. Even though maybe there is, of course, it's very interesting. So this model has a gauge symmetry, conjugating the matrices. It has a supersymmetry and this global symmetry. It was proposed originally as a constructive definition of type 2B string theory on flat backgrounds. It has many solutions, so the solutions essentially correspond to the type 2B branes, and you get the gauge theory on these solutions, at least if you equip them with a B field, and then in this way you see the relation with type 2B string theory. For example, if you compute the interactions between these branes at one loop, you pretty much recover what happens in the supergravity, at least in some linearized regime. Okay, so this is a well-known story. I will not talk about that anymore. So I would like to try to get real physics from this model. So 3+1 dimensional physics from this model. Of course, a priori it's 9+1 dimensional, and I'm not interested in 9+1 dimensional gravity or whatever. I want to see how can I get 3+1 dimensions. Okay, so here's some messages that I am convinced of. So the first message is we should not try to compactify this model. There have been proposals, contactless Schwarz and so on. So it's possible formally to compactify them. It's a nice construction actually, but then what I will talk about will not work anymore, because if you do that, effectively you introduce infinitely many degrees of freedom per volume. It's unavoidable. And then just all these loop computations that don't work anymore, everything will diverge, and what I will say doesn't work anymore. Other things will work, of course. Then you see a lot of relation with string theory, of course. Of course, it's interesting from that point of view. But for me, this is a message: don't compactify. And what the second way compactify. Well, what contactless Schwarz do? They put the torus. So take six matrices, and there is this relation: XA is equivalent to XA plus R whatever times unit matrix. And you can make this is a well-defined thing, but you need an infinite dimensional Hilbert-space intransversal direction. That's what it is. And I don't want to do that. And I claim I can get 3+1 dimensional physics without doing that. And that's the main message. And I think that's also a message for string theory. But in string theory, this is, so in proper string theory, quote unquote, it's more difficult to see what I'm going to talk about, because it's a totally opposite regime. But so that's what I think is interesting. And in this way, of course, well, another reason why I don't like this compactification is because once you do it, you don't have a matrix model anymore, and you lose the non-perturbative definition. It becomes a field theory on the torus. It's interesting, but it's no longer non-perturbative. It's just a totally different game, and you enter the landscape issue of string theory and so on. So I will avoid that, and there will be no landscape issue, and it will be hopefully non-perturbative. Okay, so that's the first message. So instead, how do you get 3+1 dimensional physics if you don't compactify? Well, go to a non-trivial vacuum. So like in field theory, assume there is something like that. So it's more, consider it metastable if you like. Let's assume that there is a non-trivial background which somehow dominates fluctuations around it. And then on such a background, the fluctuation will describe a gauge theory, and the background will describe spacetime. So the background is a brane. I will choose by hand a 3+1 dimensional background. Well, there is a good reason for it, but anyway. And then we get the 3+1 dimensional gauge theory on the brane. And I will just consider the weak coupling regime of that gauge theory on the brane. So the matrix model itself, of course, doesn't have a weak, strong coupling thing because there is no meaningful coupling model. But once you're in a background, you can talk about weakly coupled and strongly coupled, and that's what I mean. And the nice example, the easiest example, so you all know that because just take the BPS states, which is given by Moyal-Weil quantum plane in the IKKT model. These were some of the first solutions that people have considered. What you get is you get n equal 4 non-commutative superunions, and that's a perfectly fine theory. And it has a well-defined coupling constant. You can choose it to be weak or strong. It depends on your choice of vacuum. So that's the point. So I will just focus on those vacua where this gauge theory is weakly coupled. And what I will say is very similar to this n equal 4 superunions, but a little bit more complicated background. That's all. And in my case, it will no longer be BPS, but in that case, it is BPS, and then it should be beyond discussion that this really makes sense. And I'm extracting this, so in my case, you can debate it. Maybe it doesn't make sense, but at least there is a chance. Okay, and then I claim that on nice branes, at least you get some sort of an emergent 3 + 1-dimensional gravity, and you get a good quantum theory. And you get a good quantum theory because it is 3 + 1-dimensional, because then it's UV finite. If you take a higher dimensional brane, it will be no longer UV finite, and it just doesn't make sense anymore. So there is a mechanism to prefer 3 + 1 dimensions. And this is, of course, also related to the numerical simulations that Nishimura-san and collaborators, Tuchia, Costas, and so on are doing, and we will hear about this later. So now the next question is, what type of vacuum should you choose? Many possibilities. The first choice, well, you could choose commuting matrices. Of course, it's a perfectly reasonable choice. This corresponds to a lattice. But I don't like it because if you choose a commuting matrix background, you get a lot of zero modes. So basically, the location, the eigenvalues of each of the lattice points, you can shift it and you get the same action. These are zero modes. So you get a huge number of zero modes. So in some sense, that's not a good thing. So yeah. At the classical level, it doesn't make sense. You have zero modes. You have to, maybe you can handle the zero modes in some way. It's a non-trivial story. Maybe Kawai-san will talk about it. But okay, so I sort of prefer choosing not commuting lattices, but non-commuting lattices. And also, I think it's reasonable. Non-commuting lattices should dominate the path integral because the stabilizer of commuting matrices is U1 to the n. So the volume in phase space is much smaller. If you have non-commuting matrices, the stabilizer is much smaller, so the orbit is much bigger, so it should dominate the path integral. So I think non-commuting matrices.
Just to clarify, when you're talking about the commuting matrices, you are choosing a basis.
Yeah, exactly.
So you are suppressing the joint van der Waals associated with those commuting matrices.
No, of course I take this into account. Sorry, for commuting matrices, yes, I choose a basis, which is the common diagonal.
But you throw away the van der Waals, the diagonal.
No, of course you have to do it properly, but still, the van der Waals determinant will actually give you the volume, of course, of that big orbit, and
it causes the eigenvalues to blow up.
But still, no, of course, yeah, this is taken into account, but still, if you take many commuting matrices, the overall orbit, so if you act with the gauge group UN on the set of all of these matrices, the stabilizer is U1 to the n. And that means the dimension of the orbit is reduced by n. While if I take the non-commuting matrices, the stabilizer is much smaller, therefore the dimension of the orbit is much larger. That's what I mean. And that is somehow, I mean, the van der Waals, I have many matrices, so it's more complicated van der Waals.
Excellent, I think was motivated by some work of Davis and Sean Hacknell some years ago. We found that the eigenvalues blew up into spheres if you had more than 3 of them.
Eigenvalues blew up into spheres in, I don't understand.
For commuting matrices, due to that van der Waals.
I'm not sure what you mean.
We can discuss it after.
Anyway, of course, you may just, anyway, that's just my motivation. So I like non-commutative matrices. I want to focus on non-commuting matrices. Now, still, there are different possibilities you could choose. So one interesting choice of non-commuting matrices is actually, well, take some differential operators. And I think Kawai-san will talk about this. For example, take some differential operators in R4. Those are non-commuting matrices, perfectly fine. You'll find solutions in this form. This is certainly very interesting, and we'll hear about it. But I prefer not to do that because, first of all, you will still have infinitely many degrees of freedom per volume. You do get higher spin theory unavoidably because you have to include all operators. It's unavoidable. And the issue, of course, is I think we will debate the issue, of course, I think in the end of the day, you will still find those. I think we haven't completely agreed on that, but anyway, it's an interesting possibility. So we'll hear about this more, especially if you restrict to volume preserving diffuse, it's more interesting, but I don't know. I still think it's better to use quantum spaces in the sense of quantized symplectic spaces, because the main reason is because then you can maintain the having only finitely many degrees of freedom per volume, and that's, as I say, is essential.
In which sense do you mean? I mean, taking differential operators. In which sense they are measures?
They are operators on a Hilbert space. So
That's
a differential operator acts on some square integral function or something. It's a Hilbert space, like in quantum mechanics.
Okay.
Yeah. So it's an infinite dimensional matrix.
In that sense, I mean, you are picking and choosing. I mean, trying to pick non-commutative space, non-commutative matrices, commutative matrices. I think this choice should be dictated by the model itself. I mean, given the model that you have, the IKKT model, whatever model you have, I mean,
of course,
you sit in one place, in one corner of phase space, and you decide. It's not your decision. It's what you have.
The model should dynamically decide it.
What is the vacuum that you?
I know, but it's difficult. It's difficult to understand what the model tells you. And Nishimura-san, they have been working on this for a very long time. I agree with you. But I think it could also happen that there are many possible vacua which are almost stable, and the model doesn't give you a totally unambiguous. Maybe there are. I mean, the story is complicated.
The way you are looking at it, I mean, I would have thought you would start from quantum spaces. You quantize the symplectic geometry. You write a quantum space, and you write a matrix model for that.
No, I don't do it. I start with the matrix model. The matrix model has many possible conceivable vacua, and I will discuss that, and I will want to explain why I think the non-commutative spaces
are embedded in those.
Are the solutions, but I will never touch the model. It's always the same model. So the model gives you gauge theory on many different spaces. You can choose a fuzzy sphere, you can choose Moyal-Weil. It's always the same model. So I will not touch the model. I do not want to construct a model for a given space. I think that's the wrong thing to do. That will be the model is background independent. Yeah, and the background is a vacuum of the model. The model should tell you which vacuum is preferred, but that's complicated.
Exactly.
Yeah, but it's too complicated. Yeah. So I'm trying to guess reasonable vacuum of the model. That's all I can do.
I mean, it seems to me that you are conflating two things. You're starting from a model and you're trying to derive the geometry from it, or you quantize the geometry and you write a matrix model.
No. The second, I don't want to do the second thing. I start with the model. I try to find a good vacuum, which is a solution, which is difficult. So I just study what could happen. And I claim that these are good candidates for vacua. But in the end of the day, of course, the model should tell me if I'm right or wrong. Absolutely. But I'm not so far. So, as I say, I will focus on these non-commutative matrices. By the way, in particular, I will consider a covariant quantum space, which Alessandro will explain to you what it means. There you also find higher spin modes, so it gives you a higher spin theory, but that theory is free of course. So I think that's a precise statement. This I can prove. So I think it's a very good candidate. Actually, you can, even this covariant quantum space that I will talk about, you can actually consider it as a differential operator, but it's a differential operator acting in 3 dimensions, not in 4. So it's kind of hard to see, but it's actually true. We can discuss it later. Anyway, just wanted to make this remark. And again, I think 4 dimensions is preferred because only then it can be ultraviolet finite. By the way, how much time do I have? I started a bit late.
You have 20 minutes.
Okay, yeah, so I should start to, okay. Let me be a bit more specific. So what kind of branes can you have? The classical model gives you a classical equation of motion, which looks like that, which has many solutions. I will basically consider space-time branes to be embedded along the first 3+1 matrices, so you can put the rest to 0, and then the fluctuations around such a background will give you some sort of a non-commutative Yang-Mills type gauge theory. But we will have to add also transversal matrices, so actually it's essential to consider to pretty much use all the matrices. So the remaining transversal 6 matrices, I will also give them some non-trivial depth, and that will describe some compact fuzzy space. So that's something similar to compactification, but it's not compactification, but there will be, because this will be finite dimensional matrices with a finite Hilbert space. And that's actually, it turned out this is essential to get gravity. If you don't put this K, you don't get gravity. And yeah, so that's the kind of configuration that I will consider. Here's a very brief reminder why on such a background you always get the Yang-Mills gauge theory. Even so, let's assume it's so sort of, yeah, this is the structure of the background. This could be some antisymmetric images here, while or not. You take the background, you add a fluctuation, you plug it in the commutators, you get the field strength of the Young. So the fluctuation is governed by the Young-Mills field strength, and then the action, the classical action is something like the Young-Mills action for the fluctuation. So this is extremely simple. You get it for free, and it transforms as a gauge field should transform. So everything comes out for free. It's very nice, but actually it doesn't work. It doesn't work because of UVR mixing. Only in the IKKT model it may work. So which is the maximally supersymmetric case, because then n equal 4, that seems to work. That's the only. So this is very simple, very well known. Some more remarks. Now, okay, some different choices of these branes could be. So there's a nice class of backgrounds which, let me call them covariant quantum spaces. They have nice covariance properties on the symmetry group. The first example is the fuzzy sphere, which you all know. Means, let's assume that the background expectation value is given by some angular momentum generators. Of course, that's not the solution of the model. Let's just pretend it's the solution. Take this as a background. Then there is a global SO3 symmetry of the mod. So the mod has a global symmetry. The vacuum breaks the symmetry, spontaneous symmetry breaking, you get a Goldstone boson, or something like a Goldstone boson. And the Goldstone bosons of this spontaneous symmetry breaking essentially are Young-Mills gauge fields. Now it's not exactly, it's a bit of a stretch of the standard story, but I think morally that's what happens. And the point is you actually get only two massless fields, because these fluctuations, if you think about what it is, the transversal fluctuation is a scalar field, this one does get a mass. And the two tangential fluctuations, they stay massless, and this is the moral reason why they always stay massless. And the reason why I emphasize this, if you start doing loop computations, and nowadays people, in fact also buddies, was doing loop computations in these models, of course you find a mass term, AA, at one loop on this background. That's strange, how can this be? It's a Young-Mills gauge theory, you find a mass term. But the explanation is, this mass term, it just shifts the background, it changes the radius of the fuzzy sphere, and then around the new radius, still the tangential fluctuations are still massless. So therefore, in this sense, in this matrix model, finding a mass term at one loop does not mean that your gauge field is massive. I just want to have to make this message. So it's very easy to see for the fuzzy sphere. Same thing happens on the 3+1 dimensional covariant quantum spaces that we'll talk about. These are my favorite spaces. Again, there is a spontaneous symmetry breaking. The type of background matrices is a bit different, but Alessandro will tell you what it is. There we have a global SO3-1 symmetry, which is again broken by the background. You get again some sort of a Goldstone mechanism, and then the Goldstone bosons are the gravitons, I claim. And this is the reason, again, that these gravitons will remain massless, even though if you do the loop computation, you find explicit mass terms. But it's the very same reason these mass terms will change the parameters of the background, but at least some of the modes which are gravitons, they will remain massless. And I think that's pretty solid. Okay, that's another message which I wanted to make here, and you'll understand later in the afternoon why I say this.
Do you consider just IKKT action when you consider
just IKKT? Yeah, so these are, none of these are solutions. So I'm always a bit stretching some arguments. Yes, you're completely right. Strictly speaking, they're not yet symmetric. I'll come to that point. Okay, but the loop computations you can still do, even around the background, which is not a solution. You can do loop computations, and then you find these things. Okay, now moving towards gravity. So given a matrix configuration, you can find an effective metric. I've told this story many times. I think you all heard it a few times, so let me go through it for you very briefly. So take any fluctuation on the background. For example, a transversal matrix would then be governed by this term in a classical matrix model action. Now the commutator we can consider as a frame. So there is an effective frame, which is the bracket between the background and any local coordinate that you choose. Now I'm going to the semi-classical regime. And then these double commutators, you can write it in terms of an effective frame, and it assembles into the standard form of a kinetic action for a scalar field. And the effective metric is just a contraction of this effective frame, and there is a dilaton. And so this is how you identify the effective metric. I think that's a very easy story. One interesting point is that the effective frame is always divergence free. Out of this construction, you always get divergence frames. That is interesting because that's the first difference to GR already. So first of all, there's no local Lorentz transformation because the frame is divergence free. That's not a disaster because that's just what it is. So you get more degrees of freedom than in GR. Fine. And still, this is the universal metric which will govern all the fluctuations. So that's what gravity does. Okay. Now, by the way, this is an easy computation. Yeah, let me not go through that. Now, it's a good idea to work not with the Levi-Civita connection, but with the Weizenberg connection associated to that frame. Technically, it's a good idea. What is the Weizenberg connection? By definition, that's the connection where the frame defined by the matrix background is flat. You can always do that. You have a flat connection, but you have torsion. So all the information is not in the curvature, but it's in the torsion. Doesn't matter. It's just a different way of looking at it. You can compute the torsion, standard definition. It turns out that the torsion has this nice structure. That's the reason why it's useful here. The torsion can be written as a commutator of the commutator of the matrices. So take the commutator of the matrices, you get the tensor theta. Take a commutator with coordinates, you get the torsion. You can show it's a simple computation. I don't want to go through it. So that's why this torsion naturally comes out here, and it's a good idea to work with it. Don't want to spend time with these details. Then you'd start to do loop computations. And then the basic statement is just that if you do loop computation around a background which is not flat but has some curvature, then you, of course, get an induced Einstein-Hilbert action, which comes in terms of the torsion, which I just told you. That's the reason why it is important. It's just a simple computation. I will just show you. And you can compute the Newton constant. The Newton constant turns out to be the Kaluza-Klein scale of those compact extra dimensions that you have to put. So it's finite, and that's the reason why you have to put these extra dimensions, otherwise you wouldn't get the Newton constant. And if you wouldn't put the fuzzy space, but if you would compactify with infinitely many degrees of freedom, this would diverge. So that's the reason. This is finite because you have only finitely many degrees of freedom and your background. Okay, how do you do this one loop computation? Well, or how do you quantize the model a priori? The general concept of quantization, Nishimura-san will talk about this. You just do you integrate our matrices. You have to somehow make sense of the oscillating thing. There are various ways to do that, and then you can compute one loop. And because of supersymmetry, the one loop effective action starts at the fourth order term, which is kind of familiar for an Fourier pyramid. So basically, you're doing this with matrix language. Let me know.
What is the second term you added to the?
Sorry.
The second term you added to the IKKT. What's that?
Oh, that's a regularization of the. So this is an oscillator integral. You have to define it. So I put an I epsilon basically, such that I shift the contour a little bit. It's an infinitesimal bit rotation, if you like. Now it's a well-defined thing, and that corresponds actually to Feynman I epsilon. That's exactly this. So it's just to make sense of that. I mean, June has a slightly different way of doing that. I think here, actually, I prefer now your way, but it's the same. It doesn't matter. So you have to do something like that, then you can compute. In practice, to do the computation, it's a good idea to use a basis of sort of localized Gaussian wave packets. These are technicalities. I don't want to go through it. The only thing I want to point out to you that during this computation, the structures that you need to do, where is again the action? You see here there are lots of commutators of the theta, which is a commutator with something, and you have to take the trace over these things. And the way to do it is exactly, this is why you get such, this is where the torsion comes from. So in doing these computations with a Gaussian wave packet, you find the contraction of a torsion, and you can compute the trace in a reasonable way. Let me not go into these technicalities. Now, if you do this computation with this technology, and if you don't put a compact space K, then you don't get the gravity action. You start with a four derivative action, and that is actually a very strange action. I don't even want to show it to you. That's not good. So, but if you put a compact K, as I told you before, then you get a new term, which is a mixed term between K and spacetime, and that leads to an induced Einstein-Hilbert action. So it's kind of a quantum effect interaction between K and spacetime, something like that. You do the computation, you find the contraction of a torsion, and you can rewrite this effective action as an Einstein-Hilbert action.
What case leads to the fourth derivative?
Yeah, you have four commutators.
I see if you don't, if you just
if I don't put K. if I just put just a space-time brane and I leave the 6 transversal matrices to be trivial, then you have these 4 commutators, and you can only be space-time commutators, so you get 4 derivatives along space-time. But if I put K, I get 2 derivatives along space-time, and I get 2 commutators along the compact thing, and then you get the answer Hilbert action plus some extra terms. So there is an axiom, there is a dilaton, and so on. But you do find the answer Hilbert action with this with the Newton constant.
You're considering Lorentzian metric.
Yes, Lorentzian metric.
Is it important in this story?
Is it what?
Is it important?
It's probably no. Formally, you could do the Euclidean thing, but as you know, it's the model wants to be Lorentzian. So yeah, no. Formally, it is not.
And the epsilon you introduced as a liberalization that breaks Lorentz symmetry. So that's why I'm.
No. The epsilon breaks it mildly, but actually, I think this doesn't make much. This is not a big issue in my opinion. There are other effects which are more serious. Now, okay, so what you find, summary is, so gravity is, in that sense, is a quantum effect on quantum spacetime. So that's a punchline, if you like. They don't need to quantize the answer Hilbert action. Of course, string theories also don't quantize the answer Hilbert action. Fine. So in the effective one-loop effective action, you can compute the Newton constant. It is determined by the Kaluza-Klein scale of the x dimension. Now you have to ask, where does this come from? We'll talk about that, or Alessandro will talk about how to get the k and how to get this k. That's an interesting story, of course. Now you can also compute the vacuum energy. Of course, there is a vacuum energy, but it's a bit different from it's not a cosmological constant because there is a dilaton. The dilaton enters. So the vacuum energy is there. It's probably large, but it's not just a cosmological constant. It has more dynamical content, but it's complicated. I will not say much about it, except that, of course, it's important to stabilize the background. So to get a consistent background, you will need to include one loop, and then that is we'll discuss this later. But what I want to discuss in the last 5 minutes, how much do you have?
You have 10 minutes.
Great. So in these 10 minutes, I want to discuss one, I think, physically interesting thing, which is how does this gravity differ from GR? And there is a very interesting story here, which I would like to explain. It's not yet published, we're discussing it. So I would just want to give you some hints. There will be some modifications of gravity in the infrared regime. It's probably a cosmic regime. And so what happens? The point is that you have the Einstein-Hilbert action, but you also have the classical matrix model action. And these two things, of course, are combined. And that's a strange thing. So you have to start to understand, what does it mean? So the fact that it's different from GR, you can say, or forget about it. Or you can note that what we know about cosmology is very, well, at face value, cosmology tells you that GR is wrong. Well, you have to introduce lots of things to fix it. Maybe it's correct, maybe it's not. At least one should be open-minded, that's all. So probably both GR is wrong, in my opinion, but there may also be extra stuff which we haven't seen. So but one should be open-minded, and we will see some mechanism to get extra behavior for free without introducing some degrees of freedom. Well, they're introduced in the model. So I will now, first of all, I'll assume this nice type of covariant quantum spacetime, which Alessandro in the afternoon will say a little bit more about. I will avoid these technicalities. I just want to claim that this gives you sufficient degrees of freedom for the gravity. So all the graviton modes we have, actually we have more graviton modes. So the graviton also has a longitudinal mode here, it turns out. And it's also extended by a higher spin stuff. So it's a complicated thing. So let me try to focus on the simplest, most classical degrees of freedom and how they differ here from GR. So I will assume that there is this compact space K. The stabilization of this K, Alessandro will talk about in the afternoon. We have some interesting mechanisms there. And now I want to discuss the qualitative aspects of the modified gravity. So that's an ongoing collaboration with Kawai-san and Pan-Ning Ho. We don't yet completely agree, so what I say is what I think. It's still in progress, but I think it's an interesting story. And also there was a paper with Kashendra Kumar last year, which is interesting. So now I will be a bit technical. I just want to explain you why. So what I'm doing. So you have an action which is a combination of the one loop Einstein-Hilbert action plus the matrix model action. The matrix model action is a difficult one because the matrix model action looks like that. Let's consider I want to derive equations of motion. So you make a variation of the matrix model action. You get this kind of thing. This is the variation of the matrix, and these are the remaining matrices. What is this? This is not written in terms of the frame. So how can I make geometric sense of this? The trouble is that the frame is a bracket with the background. So it's a derivative of the matrix. And here you don't have that. So this thing, the Y, the matrix is a non-local object in terms of the frame. That's very strange. How can you handle that? I think one nice way to do it is you introduce an unharmonicity tensor by the following equation. So whatever is this triple thing, you can always find a tensor C, I claim, with two indices, such that this, if you take the bracket with X, you have this identity. You can typically solve this for C. In fact, it's not unique. You have a freedom. You can modify this C by any such thing, by an extra C object. And this freedom, by this new C object, is actually the Lagrangian multiplier, which comes from the divergence constraint for the frame. So it's understandable that you get this kind of ambiguity, because I cannot make the variation with respect to the frame, because the frame has a constraint, so you need to introduce Lagrangian multiplier. That's essentially what comes here. So now, let me rewrite this equation, the first variation of the matrix model action, using this unharmonicity tensor. Let me use the definition here. So the first three brackets now look like that, and this is the variation of the frame. Now I do partial integration. I move the bracket with X to the right-hand side. Then I get this object, and this object is the variation of the frame. That's what I want. Now I can write this in terms of the variation of the frame times this unharmonicity tensor. That's the reason for doing it. And now I can combine the two actions and derive the equation of motion, which is the modified Einstein equation. But you should notice that this unharmonicity tensor is some sort of an effective energy momentum tensor. But it's not from matter, it's just a non-local geometric degree of freedom. But it behaves like an extra energy momentum tensor in the equation of motion. And then you find the modified Einstein equations. So the Einstein tensor is the usual meta tensor, which is the fermions, I didn't write them down, plus this extra energy momentum tensor coming from this unharmonic structure, and there is extra stuff from Didina axiom and so on. So this is what you find fairly generally. This we did in a paper with Kumar. Now, what does it mean? What does this extra energy momentum tensor mean? To understand, so I claim it will sort of behave like, if you have some actual physical masses, this will behave like some halo-like thing around these masses, which is somehow reminiscent of dark matter. I don't want to make any claims, but at least that's what it seems to do. And it's governed by a non-local equation. And it's very hard to understand. So the only thing I can do is, let's linearize it. So let's assume that the background is background plus small fluctuation. Then the cubic matrix, so the double commutator of the background is essentially the box of the fluctuation of the matrix. Also, the frame is the bracket of the fluctuation with X. And in this case, the unharmonicity tensor is roughly speaking something like that. You see here is a box tilde inverse times the box times the frame. So this is a non-local thing, very complicated. And this box tilde is a modified D'Alembert operator, which is actually violate not Lorentz invariant, but it's rotation invariant. It's a very strange object. It's high-spin valued. But then you can solve the linearized Einstein equation. Let me quickly do that. So the linearized Einstein tensor is, of course, a box of the metric fluctuations. So now if I go, you see here, I put this term on the left-hand side, then G is the 1 times box. This is the Einstein tensor. This is the unharmonicity tensor. That's the box tilde inverse times box. And there is a mass scale M, which I will explain in the detail. And on the right-hand side, you have actual matter. Now, multiply this equation with box tilde to make it local. And it looks like that. You get the box tilde plus M squared times blah, blah. And on the right-hand side, you get the box tilde of energy momentum tensor. Now, divide by that thing, then you get non-local again. And then you get box of metric fluctuation takes this form. You can now write this in that form. So the linearized Einstein tensor is the matter plus a correction to the energy momentum tensor, and this correction of the energy momentum tensor takes this form. It's a non-local thing in terms of the actual energy momentum tensor. And there is a scale, M. M is supposed to be an infrared scale. That's a crossover scale between general relativity and a cosmic type of gravity behavior, which is modified. Let's assume that this scale is many, many light years, maybe hopefully 100 million light. I don't know. I cannot compute it. So what does this mean? Well, it means that if the if you look at short wavelengths of the graviton, then you can just ignore that thing because 1 over k will be small and you'll get the Einstein regime. But if the wavelength of the metric perturbation is very, very long, then this is basically -1, and then you get the -1, and then this thing will actually cancel, and then there is no gravity in the very far infrared. So what you find is this: at sort of shorter scales than this crossover scale, you sort of recover GR, and at longer scale, gravity gets screened and it actually cancels at infinite distances. So that's what happens here. So you have an infrared modification of gravity. And just for fun, let's put the point mass in the origin of mass capital M. So energy momentum tensor would be something like that. Let me, so what you, if you solve this equation, then you can sort of solve it. What you find is you find that this extra energy momentum tensor has a sort of 1 over funny 1 over r types of distribution around the center. Little m is a very, very small mass. So basically this is invisible. Little m is very small unless, so this is totally negligible unless this is very large. So for very heavy objects, it will behave as a long distance halo. And if just for fun, if you compute the rotation velocities around such a thing, you get the blue type of curve. So you get actually extended rotation curves, while if I drop this term, this is the ordinary rotation curve. And this is, let me just, you don't need whatever you want to think of it. That's sort of roughly speaking the kind of behavior that you get. It's interesting in the context of dark matter, but it's totally naive, of course, this computation. But you find something like that. That's all I wanted to say. So you get, okay, so the main, well, there's some issues. For example, this is a higher derivative effect, the action, so there is a danger for instabilities, tachyons, and so on. And indeed, we find a resonance. So there is a new solution here of this Einstein equation, which is the resonance. And formally, for a very long wavelength, actually it becomes tachyonic, it becomes unstable. So now we're debating it. You may say this is disaster, is unacceptable. I think this will actually be stabilized by nonlinear effects. So the treatment was very similar, very, very simplified. If you look at it in more detail, this is the fluctuation will soon enter the nonlinear regime, and then the Young-Mills action of the matrix model, I think, will actually stabilize it and avoid anything dangerous to happen, because if the Young-Mills action dominates, the Young-Mills is sort of self-limiting, and it should prevent any bad behavior, but we don't know. Another message is, so gravity is screened at long distances, which may be interesting, I know, why not? And there are also, yeah, and Alessandro will tell you some other aspects in this context. So I'm basically at the end now. Something that I didn't talk about is the aspects of the cosmological background. This covariant quantum spacetime is actually a nice Friedmann-Robertson-Walker universe with maximal. It is homogeneous isotropic. It is k equal -1. It is sort of really a nice quantum spacetime, and there are no ghosts. It is not a solution of the IKKT model. It is only a solution if you add the mass term. That's what Jun was referring to. Now, there are two things you can fix, two ways to fix it. Either you include quantum corrections, we did some computations for that, or maybe we have now a nice mechanism. If you let the k rotate in the internal space, Alessandro will talk about it, then you can actually stabilize the solution at the classical level. So including k, now one can, we have classical solutions of the model, which are very similar to the covariant spacetime that I talk about, but they are also, we're not completely happy yet. There are some issues. Alessandro will talk about that. But the mechanism for gravity is quite independent of these details, so it was kind of a more generic story. So this is why I don't worry so much about it. Now we even have an example for k equals 0. There's a recent paper with Christian Gass. It's actually even simpler. So k equals 0 is fine. You can do the same thing. It's even simpler. So I think one should focus on that. But there are lots of open issues on which one should work on and try to understand it better. Here's a collection of literature. You find it. There's an introduction in my recent book, but there's also lots of papers where you can find lots of things. So I want to stop here. Thank you.
So thanks to the organizers for organizing this. Nice to be.
Sorry for I think you know, everyone knows who you are.
The first name.
Yeah.
First name there. Nice to be back at DIAS. So this is our small research group in Bratislava. I'm just flashing it because you will see Juraj later this week, and some of you might remember Peter Presnyder, who is still coming maybe on average once a month to discuss with us, and we have plenty of students interested in matrix models, numerical simulation, bootstrapping. So if you have some interesting problem they can be doing, please let us know. And basically the idea I'm going to spend next couple of minutes on is the fuzzy onion model, which is basically gluing together multiple fuzzy spheres to fill a three-dimensional space. This can be done in many different ways. We are interested in a procedure that has good limits, which means we can basically reproduce physics in a three-dimensional space. There is a saying that good ideas travel far, and this idea traveled like 10 meters because it originated at DIAS 7-8 years ago when Juraj was visiting DIAS, and it was either in my office or in this very room when he asked if we can basically take the fuzzy spheres, put them together in a way to reconstruct a different model of three-dimensional quantum space. So this idea basically on average didn't travel at all because it started in this very building a couple of years ago. So it's a very nice place to report on the results. So this is the fuzzy sphere. Is this? I can just skip those slides, but this is just very briefly. It's a sphere with a limited spatial resolution, which can be expressed using Hermitian matrices. And the way I think about this is something that is used in a technology when you are making MP3 files. So you want to make a music, but you want to save some memory, put it into iPod or something. So there are two ways how to digitalize sound. One way is you can basically take the sound, take some points, and just measure the amplitude at those points, and then put those into the memory. The other idea is you can do the Fourier expansion and just save some of the coefficients. And the nice thing about this approach is, well, we know we humans have limits. We cannot hear sounds above some frequencies, below some frequencies, so we can just discard them and just record the parts of the sound that we can actually hear. So this is basically the idea that you can discretize a space in two different ways. One is sort of a lattice approach when you just pick some points, and the other is you first do the Fourier expansion and then remove what you cannot use anyway. Of course, in our case, we are not interested in producing MP3s. We are interested in producing some sort of quantum space which has very small length scale. One can figure it as the Planck scale, but it can be something larger. And actually, we are interested in using this model in some scenarios in which the scale can be actually arbitrarily large. So it's a parameter. So the fuzzy sphere is a sphere with limited spatial resolution, and there is a dictionary between matrices and fields living on a sphere with limited spatial resolution. You can think of it this way. You can do the expansion in terms of spherical harmonics, and then you make a cutoff. When you do the cutoff, the number of degrees of freedom perfectly fits into a Hermitian matrix of size n. And when you increase the matrix size, you have more and more information to describe the fields on a sphere. And in the limit of infinite matrix size, you can reproduce fields living on a sphere with arbitrary precision. So when you have some kind of cutoff, you can express it using matrices and also claim you're describing some geometric quantum features. So one of 2 or 3 technical slides. This is just how we define the fuzzy sphere using SU2 generators. And I'm adding this superscript just to show that we'll be using matrices of different size. So this brackets just shows you the size of the fuzzy sphere. So n goes from 1 up to basically infinity. And as n increases, there are 2 different ways. You can keep the size of the sphere fixed, and by increasing n, you are increasing the spatial resolution. So basically, the size of quantum blocks goes to 0. Or S with increasing n, you can keep increasing the radius in this way, which keeps the size of the quantum blocks fixed. So we are interested in this limit, adding larger and larger fuzzy spheres, and the quantum structure on each of the layers is the same. So by increasing n, we are increasing the radius of the sphere. Now just some pictures, because this really is a dictionary where you can just type in a Hermitian matrix and use the dictionary from this, expand the matrix in the basis of Hermitian matrices, take the coefficients and use them in the expansion of spherical harmonics. So you can take this matrix, and it translates into a field that lives on the North Pole. You can put it here. This will be the South Pole configuration. The sphere is rotated a little, so you cannot see it. This is on the other side, the South Pole. And then you can just start moving with the numbers just to get some sort of intuition. So one here is a field, a European field, basically. And then you can place one somewhere. It's probably better on that one with the color resolution. Now the good way of manipulating the states on the field, basically just use the rotation. So you can produce a field that is the North Pole field, and then you can just rotate it around to get a field that is located anywhere on the field, on the sphere. Okay, and then basically you can do physics. Physics, at least in this building, can mean doing some sort of field theory. In this case, instead of integrating over fields, you integrate over Hermitian matrices of fixed size. You define some sort of action, and you can study the phase structure of the field theory. The geometry is added by considering some kind of kinetic term. So this tells you it's the fuzzy sphere, and in the appropriate limit, you should be able to reproduce physics on a sphere. There are some difficulties with UV, IR, mixing, and so on. But at least naively, you can do some sort of physics, and you can measure or you can compute mean value of observables expressed as path integral formalism. So this is the fuzzy sphere. There are some nice things about it. It's very simple. So we can understand a lot of quantum space physics using the fuzzy sphere. There are some issues, but it's good the fuzzy sphere has the issues because you want to understand them in a simple context as possible. So it's basically nice. It emerges elsewhere. So for example, in the BMN model as a vacuum of the model. Unfortunately, it's a two-dimensional model, and we are living in a three-dimensional space. So it's a very nice and important playground to understand physics of quantum space. But unfortunately, it's only a two-dimensional model. So we are interested in having something three-dimensional. And there is a model of three-dimensional quantum space that can be expressed using two sets of auxiliary bosonic operators. Let me denote them A with a dagger. So you have two sets of auxiliary operators acting on a Fock space, or producing a Fock space, acting on the vacuum state. And then you can define non-commutative coordinates using those two auxiliary operators. And you can basically do quantum mechanics when you have the coordinate that is non-commutative defined in this way. You define the momentum operator, the Hamiltonian, and you are doing quantum mechanics. So this is how we can define the Hamiltonian. Using this, you can define the Schrödinger, the Coulomb problem, and study the Schrödinger problem of basically hydrogen atom. The spectrum has been found exactly in this way, so you can expand the square root, and you will get the famous Schrödinger result. So very good place to be to discuss this. And then there are some corrections. So there is a good three-dimensional model of quantum space that is expressed using those two auxiliary operators. And personally, I can say it's terrible to work with. It's quite annoying. You can set some calculations, but usually you end up with some differential equations of third, fourth order, and so on. And it's very difficult to get exact results. The hydrogen atom, I don't want to call it a miracle, but it's like a lucky coincidence that you can solve it exactly because many symmetries have been preserved. But otherwise, if you set up a general problem in this in this formalism, it's not very convenient to work with, and you are going to spend a lot of time basically doing anything. But it has some nice properties. Many symmetries are preserved, so many problems you can solve in ordinary quantum mechanics exactly can be translated. This model, it can accommodate magnetic monopole states very naturally. So here you can see for X, you use one creation and one annihilation operator. So if you have a wave function psi, it has the same number of creation and annihilation operator. And if you introduce a mismatch between those, you add some extra, for example, creation operators, you actually produce monopole states. So you can describe magnetic monopoles very conveniently. You can study some phenomenological predictions from these models. And it's nice because it's three-dimensional. So the hope was to find a problem, to find a model that shares the nice features of the fuzzy sphere construction. That means it can be expressed in terms of matrices, but it's also three-dimensional, sharing the features of the bosonic construction. And the fuzzy onion model is the result of this project. So it's a three-dimensional model composed of fuzzy spheres glued together. So the basic idea is very simple and it appeared many times before. So increasing the matrix size increases the fuzzy sphere radius if you keep the scale of non-commutativity fixed. And it's very straightforward how to produce a three-dimensional space from this. You just glue everything together in this manner. So you put all of those matrices into a larger one. So you are using matrix of a very specific form, which is sort of diagonal, but the diagonal elements are increasing as you go along the matrix. And again, it's better, easier to see here, but I cannot just go here. It's basically a set of concentric fuzzy spheres plugged in together. So you can do the limit, increase this up to infinity, and then you will basically fill the volume with concentric fuzzy spheres. So this idea is simple, and on each of the fuzzy spheres, you can basically just borrow the angular part of the kinetic term from the fuzzy sphere construction. So you can define it in a very straightforward way. This has been done many times before. The tricky part is basically defining the radial derivative. Why? Because to define the derivative, you want to subtract fields living here minus fields living on the layer below. But the fields here are described, for example, by a matrix 3 by 3, and the one below is 2 by 2 matrix. You cannot subtract those two matrices. And here comes the idea from MP3 technologies. You can just expand those, remove anything that cannot be heard or cannot be matched, and then again plug everything together. So the solution to our problem is just ignore everything that cannot be solved and plug it back together. So we expand we can expand this matrix in the basis of Hermitian matrices, discard some of the terms, and keep only those that can be, again, put together to form a two-dimensional matrix. So the second technical slide is this. We define two sets of operators. One is called down and one is called up. This makes your matrix smaller by 1, and this makes your matrix larger by 1. But it's basically, you take the expansion and then plug everything together using larger matrix, using basis of larger matrices, either by 1 or smaller by 1. When you can compare, or when you can map larger matrices into smaller matrices, you can define derivative, you can define the kinetic term, which is defined in a sort of like lattice way, and then you can study physics. There are some technical difficulties around this, so some ambiguities. We have just tested many different approaches, and one of them worked very well, so I'm just going to report on that one. But on each of the layers, we can borrow the fuzzy sphere angular part of the kinetic term. Then, using this approach, we can define the radial part of the term of the Laplace operator, the kinetic part of the energy, and then again we can do physics in a fuzzy sphere way. For example, we can define a field theory. So now psi's are those weird matrices of increasing diagonal components. So we can define action this way, and now we can integrate all our matrices with the probability defined by this action and study a field theory. There are two different set of results. So these are 10 layers, first, second, up to 10. And this model had 10 separate fuzzy spheres. This model had 10 layers of fuzzy onion space, which means there is also the radial derivative radial interaction. So here you can see 10 consecutive fuzzy spheres. Fields on each of the layers is living its own life. Here, when we turn on the radial derivative, we see some organization between the layers. So here you can see actually they are not independent. So the structures are going up across the layers, down across the layers. So this was the first check. The scalar field theory.
Just to clarify, it looks like you lost unitarity in because in this the way you describe it, it looks like you lost unitarity.
Unitarity in what sense?
In that
you are discarding something.
You're discarding degrees of freedom, that you can have leakage of probability or things that you projected out.
It's just some degrees of freedom are not entering the computation of the action. They are still there, but when you compute the action, it's just they are being ignored. So it's not we are discarding them from the matrix, but they are not entering the action. So the action is not feeling some of the degrees of freedom. But this is the there might be some issues, but it produces nice results. So. Okay, so when we turn on the radial part of the kinetic term, really the fields are interacting also in the radial direction. So this was the first check. We try to study, I wouldn't trust those results, but we study the phase transitions in this model. It's known that in fuzzy sphere model, if you have a scalar field theory with Portic potential, there is some interesting novelty. The eigenvalues can either be oscillating around 0 when you have the disordered phase, and you can have the uniformly ordered phase when all of the eigenvalues are in the same potential well, when you have the Higgs potential type of potential. But there is a novelty. You can have half of the eigenvalues in one of the minima, the second in the other minima. And we studied this transition in the fuzzy onion model. So here we initiated all of the eigenvalues in the same minima, and we can see half of them at the outermost layer moved to the other well, and then this process cascaded down the fuzzy onion space. I wouldn't trust those results because my students spend like 2 or 3 months gathering data and then find a typo in the code. So now the poor little guy is redoing all the calculations, but I think basically we'll be getting very similar results, but maybe something will be slightly shifted. It was a small typo, but still. So the fuzzy is
following up on Daniel's question. Is there any sense in which you can show that the pieces you're leaving out of the action are sort of one or more n suppressed or one or more n squared suppressed? If there's some well-defined large n limit here, which might be appropriate for the
next couple of slides. Because we can do also quantum mechanics in this model, and we can reproduce the other model with which seems to have a good commutative limit. Okay, now this is basically just a teaser, but with the construction, we are not constrained to do only quantum space studies. It's a different way of discretizing spherical coordinates. In this case, the angular directions are discretized in a fuzzy sphere way. The radial direction is a lattice way, and more symmetries are preserved in this way than in a typical lattice discretization of a sphere. So we can study ordinary physics. So, for example, heat transfer on a sphere. So this is a tricky. So time goes from here to here, and there are 5 layers. So first, second, third, fourth, fifth. So we initiated the model with inner layers being cold, and we placed some heat on the outermost layer on the south pole. And then we just observe how the heat propagates both inwards and toward north. So 4 cold layers, 1 heated on the bottom, and the heat dissipated basically along all of the 4 layers and towards some uniform distribution. It would be nice to have something more complicated than just a heat transfer. It's a very simple model, but for example, to have something, for example, Navier-Stokes in a fuzzy union space, because then you can do something like a meteorology using this model. And in this case, the scale of non-commutativity or the scale of spatial resolution wouldn't be Planck's length. It can be the size of your pixel in meteorological models, which is defined by how far away your measurement stations are from each other. So it can be actually 50 kilometers or something like this, and you can basically capture the spatial resolution of the model within the model. And you're describing everything using very large matrices. And humanity invested a lot of effort into manipulating with matrices of arbitrary size, basically. So computers are well equipped to work with matrices, and in this model you can express everything in terms of very large matrices. So there can be some takeaway from this, and it can be actually useful for doing ordinary physics. Okay, so the big check for us was studying quantum mechanics. So we can use the model to define the Schrödinger equation in a standard way, and define the hydrogen atom problem, solve it, and compare the spectrum. So here are the results. So these are the results from ordinary quantum mechanics in appropriate units. So this is the first energy level, second, fourth, and so on. These are the results from the three-dimensional bosonic construction, and these are the results from the fuzzy union space with rather small matrices used. And we are able to reproduce the spectrum completely. So we can define quantum mechanics as a one large matrix problem. We are searching for eigenvalues of the Hamiltonian operator, and we are getting very precise spectra. And by increasing the matrix size, basically we can approach the previous results with arbitrary precision. So it seems to be working very well.
Can I ask?
Sure.
The formula is it derived in which scheme exactly?
So the red formula is from the bosonic approach. You can either try to solve the Schrödinger equation directly, express it as a differential equation, and get this by finding some roots of hypergeometric functions, or you can just use basically the symmetries of Laplace congruence vector and get exactly the same formula. And it's funny because you actually get another spectrum with plus here. So there are two types of solutions. One of them diverges in the lambda goes to infinite limit, lambda goes to zero limit, and the other one reproduces the hydrogen atom problem spectrum. And here we reproduce the results basically exactly.
This result, you mean this formula?
Yes. Numerically with a precision that can be achieved on a personal computer. So this is just a numerical result. Is this table?
So the first line is the ordinary hydrogen atom in the table.
So this is the ordinary, and now we are using arbitrary large lambda to show the differences between those. So this is the red equation using arbitrary large lambda to see the effect, because otherwise quantum space effects on hydrogen atom are negligible. So we increased lambda to see the difference between ordinary quantum mechanics and quantum mechanics in a quantum space. And this is the results from the fuzzy union space. And we can basically, here you can see some mismatch, but by increasing the matrix size, we can get as many levels as we like. Now, there are some important regimes. So one regime is when the scale of non-commutativity is smaller than the characteristic scale of the hydrogen atom, the Bohr's radius, and the radius of the model, which is defined by the largest matrix we are using, is way larger. So the first line is something that should be in the limit of lambda goes to 0 and lambda n goes to infinity, reproduce ordinary quantum mechanics. So here we can see a comparison of the radial dependency we are getting with the one from quantum mechanics, and the match is basically perfect. We are getting the same energy spectrum. Then there is another interesting regime. in which we keep lambda on the order of Bohr's radius, which is artificially large, but we can then study the effects of quantum space on the hydrogen atom. So this is a picture from this regime. You can see it's different than in ordinary quantum mechanics, of course, and you can try to interpret something. So for example, it feels like quantum structure is pushing the wave function away from the origin. So this is ordinary quantum mechanics, and this is like a pushed away. So maybe some kind of intuition can be obtained from this. And also in the regime when lambda times n, which is the radius of the model, is comparable to the Bohr radius, we are squeezing the hydrogen atom. And surprisingly, people are studying this model a lot. Hydrogen atom being squeezed in a spherical cavity, because people in chemistry are doing this to study models under pressure and so on. So we actually noticed that in 2022, there was a paper about hydrogen atom squeezed in a spherical cavity with high precision results, because, I don't know, I have been told that people in geology and so on are interested in this kind of models to study how, I don't know, molecules are working 1,000 kilometers below the ground when the pressure is very large. I don't know. I don't want to say that. I don't really care, but I cannot judge if this is true or not. So we studied the hydrogen atom confined in a spherical cavity. So this is the radius of the cavity, and we are moving it towards the origin, squeezing the atom and seeing how the wave function is changed by this. So this is the wave function without squeezing, without putting the cavity. This is our result, and exactly matching it is the result of the other paper obtained by the chemistry guys. There was interesting feature of the hydrogen atom problem in the quantum space observed by Peter Preschneider, his other student Veronika Galikova, and myself 10 years, I don't know, many years ago, which basically you get two types of solutions. One is the usual hydrogen atom spectrum, and then there is like a mirror state of energies, which are mirrored by the Planck energy scale 2 over lambda square, some very large energy scale. That was the first interesting feature, that we got two sets of solutions, and actually they're not for the same model exactly. One of them was for repulsive potential. So you flip the sign of the potential and you get bounded states for very large energies. So something we didn't understand before. Finally, with the Fuzzian model, we can study this model a little bit. So these are the solution for a model with 100 Fuzzianian layers. This is the first energy, lowest energy state, second lowest, and so on. Then you can see something weird happens in the middle, and then it again calms down, and you get something that looks very similar, but it's flipped to the other side. When you take the repulsive potential, you get the same picture, but running from the other side. This would be the highest energetic state, and then it goes down, and this would be the last one. So we wanted to understand the symmetry, and it can be actually understood in this setting. It's similar to something people are doing in condensed matter physics. So when you have those two like pair Hamiltonians, pair in the settings, you have the free kinetic energy plus some potential or minus the potential. This can be used to describe a system to which you either add an atom or you produce a whole. So add a particle, remove a particle. So it's like having the same action plus or minus a potential. And we observed just numerically that we obtain this sort of mirroring in energies. And it can be proved that actually, yes, if you have those two Hamiltonians, you can define a new operator, we call it P, because it takes your solutions and turn them into solution of the second problem. So C is the solution of this problem. C slash or this second C is the solution to the second problem. And it can be defined that you can show that using a matrix that satisfies those two properties, the solutions of the first problem become the solution of the second problem. The P matrix in this case is actually a very simple matrix. It's just a huge diagonal with +1, -1, +1, -1, +1, -1. What is this matrix doing? If you have a state that is oscillating a very little, and you multiply it with this matrix, you will get a highly oscillating state, and the other way around. If you have highly oscillating state and multiply it with this matrix, you'll get something that is very calm. So this is basically like turning UV states into IR states and the other way around. And we can study the spectrum, which is interesting in a way because we know in the correct limit, we should be able to reproduce the ordinary quantum mechanics. And then you have two types of states. You have the discrete set of bounded states and a continuous set of scattering states. So we wanted to see how the spectrum is evolving. So we are increasing the number of matrices, slowly approaching the limit and seeing these are the energy levels versus the size of the model. And we can see that in the n goes to infinite limit, more and more states are added to the spectrum, and something that initially was a scattering state or something with a positive energy slowly goes below zero and becomes a bounded state. So as we go to the infinite limit or the continuum limit, we'll be able to reproduce. This will become the set of bounded states, and we'll still have a plenty of scattering states. Okay, and now some outlook. I keep promising this for like Harold, so this presentation like 3 times already, and always I promise we are going to look into this because, well, there is a lot of empty spaces in our matrix. So what to do with those? There is some kind of intuition that, for example, those elements, we need a Hermitian matrix, so pick those two elements. They can be maybe connecting the first layer with the second layer, because the first layer is in a way 1 degree of freedom, the other is 2. So those can be sort of stringy states connecting those two layers. Then you can add more layers, and this is something similar to the BFS interpretation or BFS interpretation of diagonal describing the position of D-nut branes and then off diagonal elements, strings stretching between those states. So this might be something similar. Since first I spoke about this, we ran some simulation of the full model, and it's promising, but it needs more time to be well understood. But now we are trying to understand if those off-diagonal elements, off-diagonal in this sense, degrees of freedom can be used to describe something that is stretching in the radial direction between the layers. Seems promising so far, but need more time. Another idea is the model, as we have defined it, has one ugly feature that on each of the layer is a fuzzy sphere model. Fuzzy sphere model is non-local in a way. In radial direction, we are preventing the non-locality in a way that the way we define the potential is a potential on each of the fuzzy layers separately. So we wanted to add some kind of radial interaction also in the potential part of the action, not only in the kinetic part of the action. And one of the things you can do is either introduce those off-diagonal elements to connect the spheres, and then we can use potential of the form with psi squared, but psi in this form. The other way we can try is this. We can basically smear the fields. So since we can take fields from one layer, put it on the layer below, so we can just do some kind of smearing procedure. So instead of taking this field, I take this field plus some average of the field below and above it. And we ran some simulation to see what is the correlation depending on how we smear the fields, and seems to be working well, but again, need more time to be understood properly. So we can add some kind of interaction also in this way, like smear the field to produce the non-locality, or introduce the non-locality by hand like this. Now, something that might be worth time thinking about is how this model can be used as a model of very simple toy universe expanding. As I described the model so far, the radial direction is a radial direction, but we can think of it as a temporal direction. So we have a small fuzzy sphere, larger fuzzy sphere, larger fuzzy sphere, and then we can define some kind of dynamics of those expanding fuzzy spheres. It's interesting in the regard that the size of the Hilbert space is increasing in time. There are some mathematical approaches how to capture this. There are some efforts in causal set theory to introduce something very similar, adding new degrees of freedom to the model to describe an expanding universe. And it can help us try resolving some features. So, for example, if the universe is expanding, the universe is expanding, but if it is composed of small Planck scale cells, what happens to the number of Planck scales? Does it mean with the universe expansion, number of degrees of freedom or the number of Planck cells is increasing? Or does it mean the size of Planck cells is increasing? Probably not if they are defined by the constants of nature, but maybe we don't understand them properly. So we can maybe use this model to try to understand some features of the earliest cosmologies when the number of degrees of freedom might have been drastically changing. So the outlook is do a proper field theory to understand what is going on, try to finally understand better the string state formalism. It was very fruitful in the case of the fuzzy sphere, of a single fuzzy sphere, so there is probably no reason why it shouldn't be fruitful here as well. Try to see the connection to other theories. So 7, 8 years ago, still like in this building with Denjo and Yuma, we studied the BMN model, the supersymmetric version, in which some of the vacuum is basically a set of fuzzy spheres, but not of increasing radius, but of some radii. So we can maybe check if there is some connection between those models, and if we can maybe get some inspiration from the BMN model, how to connect the letters together. Try to do some classical or astrophysical application using this model. So I mentioned this is a difficult problem, and I don't want to start it, but some kind of Navier-Stokes equation in a fuzzy onion model, but maybe something simpler like gravitational collapse, something spherically symmetrical, and see how are singularities formed during gravitational collapse, something like this. And the most difficult task, get other people interested and test the model and see if it can be useful for the thing they are studying. Thank you for your attention.
Yeah, thank you very much, Benjamin. Thank you. Thanks to the organizers for inviting me to come to this workshop. So it's my first time at DIAS. I already came to Trinity a few times to discuss for workshops and to discuss with my colleagues from who are working on holography, integrability, and so on. But I was never here. So I have a background in integrable models, 1 over R square Calogero models, which are of course more related to matrix models. But in the last 20 years or so, I work also on integrability applied to holography, to ADS-CFT correspondence. So today I'm going to tell you about this activity. I will focus on correlation functions in this integrable supersymmetric gauge theories, like n equals 4 super M meals, the commutative version, and theories which are related to it. And so I'm going to mention present a recent work with Shota Komatsu and with my student Guanael Ferrando, with my former students, my student Gabriele Fundes, my former student Guanael Ferrando, and also based on some previous work from 6 years ago with Ivan Kostov and Valentina Petkova. So in this recent work, we found a connection between the approach integrable approach to correlation functions in these theories, and results obtained by localization. So I suppose I would like to give a motivation for this type of work. So I was mentioning holography and the relation between strongly coupled gauge theory and string theory is a long-standing problem, and a lot of progress was made since the mapping between n equals 4 super-young mills and the strings on ADS ADS 5 times S5 background, and this duality was it's possible to study in a precise manner thanks to integrability, which was discovered around the years 2000 in a series of works, among them an important paper, an important work which serves to exploit the integrability for any value of the coupling constant in this theory was, of course, the work of David and his collaborators, BMN background, the introduction of BMN background, which is also behind the BMN model. So this integrability became since an important tool of exploring this this duality, and also to compute objects that are, for example, Feynman integrals that are important for concrete physical problems. So this this mapping between between the objects in the n equals 4 super-young mills theory and an integrable model, an integrable spin chain, is done in the most transparent way by looking at the gauge invariant operators in n equals 4 super-young mills. So you take some fields. I will explain a little bit better what these fields here are, but these fields are NC by NC matrices. I will take the limit where NC goes to infinity. So we take this product of matrices at a particular field in R31 in the Lorentzian space, and we take the trace over the gauge group and build some gauge invariant operator in this way. So this object is made put in one-to-one correspondence with some state of an integrable of a spin chain. So you consider that these Z operators are some type of state of this abstract spin chain, and then the others are let's say X correspond to some other position of some other configuration of the spin chain. So this mapping here is what is behind this correspondence between n equals 4 super-young mills theory and spin chain. And also there is a relation with this description of the spin chain and strings in the ADS5 process 5 background. So I suppose many of you were already exposed to this kind of talks, so you already encountered this correspondence. So I will say a little bit more about it in the introduction of a review of the ADS CFT integrability. And then I will concentrate on ways to describe correlation functions and make n equals 4 super-Young Mills, some geometric decomposition of these correlation functions, which is inspired by string theory, let's say. And then I will mention the works that we have done, the work we have done with Ivan Kostov and Valentina Petkova in computing one of these correlation functions as a Fredholm determinant, and introduce an object that that appears repeatedly in this activity. And then I will switch to a deformation of n equals 4 super-Young Mills theory, which is an orbifold, ZK orbifold of n equals 4 super-Young Mills. And this theory was studied a lot by supersymmetric localization. In fact, the BPS sector, the supersymmetric, the vacuum sector was studied a lot by supersymmetric localization. And there are results for correlation functions of this BPS operator from obtained by this methods. And our recent work was to compute, to reproduce this 3-point function from with the integrability methods that I will introduce in my talk. So to review what I was saying about the ADS CFT spin chain. So I was saying that I put into correspondence gauge invariant operators, local gauge invariant operators in n equals 4 super-Young Mills to a spin chain, which is a long-range generalization, supersymmetric, also of the isotropic Heisenberg spin chain that is usually used to describe magnetism in one-dimensional magnetic systems in condensed matter, and which was proven to be integrable almost 100 years ago. So as I was saying, our spin chain is deformation with a continuous parameter, which is given by the 't Hooft coupling constant. So I will send the number of colors of the gauge group to infinity, keeping this combination of Young-Mills coupling constant and the number of colors keep it constant. So my parameter will be the reformulation of the 't Hooft coupling constant in this way. Well, the fields that are the fundamental fields of my n equals 4 super-Young Mills theory are bosonic fields, these phi i's, 6 copies of them, 4 copies of the fermions. So this the fields are mixed between themselves by a symmetry, by the action of SU6 or SU4 algebra. And then we have the gauge field and fields and the covariant derivatives, which are also part of the big super multiplet with the other fields. So there are 4 copies of the supersymmetries, which will mix. In fact, the theory is conformal. This n equals 4 super-Young Mills theory is super conformal. So there is an action of the conformal group, which is this SO4 part, and together with the supersymmetry, they form a super algebra, which is PSU22/4. So this is also the isometry. I mean, the bosonic part of this supersymmetry algebra is also the isometry of the background in which the strings lives. So the symmetries between the n equals 4 supermills and its holographic dual are of course the same. So I was saying that there are 6 copies of these bosonic fields. So it's useful to make some complex combination of them. So I will call one of the complex combination Z. So there will be a Z bar with if I take the minus sign here, and the different complex combination will be called X. So if I take X bar, will be the combination with a minus sign here. So if I take just these two copies, these two copies of bosonic fields will form a SU2 subsector of the bigger spin chain. So sometimes it's useful just to think about this as a spin SU2 spin 1/2 spin chain, as I was saying, to make the comparison with the isotropic Heisenberg spin chain. So inside this whole space of states, there are some states which are particular in the sense that they play the role of the vacuum state of the spin chain. For example, the ferromagnetic vacuum of the Heisenberg model. This will correspond to traces of one of these operators taken to the power n. In fact, it's hugely degenerate because it's a SU2 invariant, so there are more states which are degenerate with it, and this sector will be called this is the vacuum sector. The energy is 0, and it corresponds to the symmetry protected states in the gauge theory that I will call BPS. So in the spin chain formulation, the states are described in terms of spin waves around this vacuum state. So these spin waves are called in the spin chain language, they are called mesons, and they have their own. I mean, they have flavors because we have a huge symmetry group here. So Z breaks this symmetry PSU224 down to two PSU22s, left and right. So the spin waves which are created above this vacuum will have this PSU to the left, PSU to right matrix structure, and the scattering matrix. Once you say that these objects have their own life, they scatter two to two. They have a factorized scattering. Then the only thing that is left to do is to compute the scattering matrix, and this is something that Weisert computed almost 20 years ago. It's fixed just by supersymmetry. So once you do this, and then you can use the technology of Bethe-Ansatz in order to compute the spectrum of the anomalous dimensions of the theory just by using the symmetry and the equations that are obeyed by the momenta of these excitations, magnums, of these particles. And of course, it's very easy to. I mean, the approach works beautifully when this length is large, but then when this length is small, you have some finite size correction, which are related to the fact that the spin chain is long range, so there are some effects of how the interaction, long range interaction of the chain plays with the length of the spin chain. So this it took almost 1 decade to understand how to compute this finite size correction via reformulation of the thermodynamic Bethe-Alsace technology, and it is packed now into what is called the quantum spectral curve approach. So this story is about computing the anomalous dimension of the theory. So if you are thinking about correlation functions of these operators that local gauging invariant operators that I was alluding to earlier, so what you can compute by computing the spin chain energy is to compute this dependence of the conformal dimensions with the coupling constant here. But if you want to solve your theory, to find all the information about the theory, you also want to look what happens when you compute higher point function. For example, the next quantity to compute is the 3-point function. So you have in this string, dual string interpretation, this will be interaction between 2 strings. So you have 3 operators and you connect them by 3, which can be represented by these 3 closed strings here, and then you have to make them interact. The space-time dependence, of course, is fixed by conformal invariance, and then what is left is to compute this structure constant here, dependence with respect to G. So this structure constant, of course, is dependent on the initial data about these 3 different incoming states. So that's typically that's one of the problems that we approach in this. We want to compute. Also, we can have any number of points here, but in principle, through OPE expansion, you can imagine that you compute a higher point function by doing OPE decomposition, and once you have the structure constants here, you can do everything.
What characterizes the long-range interaction in the spin model? Sorry, it's my ignorance. I don't know.
Yeah, no. So the range of the interaction is controlled by the coupling constant. So if G is 0, you only have nearest neighbor interaction, and then when you switch on G, for each power of G square, in fact, you get more and more interaction. So like 20 years ago, we were playing with different integrable models that have this characteristic. So the one that is most closely related is the Hubbard model. If you want to obtain Heisenberg from Hubbard, you can do this. Hubbard model is a model of fermions that jump on a lattice with a local on-site Colombian repulsion. So if you send this Colombian repulsion to infinity, then by reduction you get a spin chain. Especially if you have the number of fermions equal to the number of sites, you see that you cannot have, you will have exactly 1 fermion per site, so you get a reduction. So the Hubbard model the Hubbard model has a structure which is similar to this. So the dependence in the G is similar to the dependence on 1 over U.
Before you go on, can I
Yes, yes, sure.
on the A-squared side, why do you restrict yourselves to the operators constructed from X and Z only and neglect 5, 5 and 5, 6?
Well, it's just for pedagogical purposes. In fact, when we are
so here you define Z and X, but
yeah, but
there's no 5.
yeah, in general, we'll. So you see, if I have only Z and X, the charge carried by magnon will be U1. But in fact, here I consider all of them. Yeah, but this was just to remember the connection with Heisenberg.
So if I worry about a non-BPS operator like Konishi, then I would need all of them, right?
Yeah. So Konishi, for Konishi, this question of finite size correction is very important. But of course, we have results from this approach for Konishi for I don't know, the 20 orders in G squared.
But then what does it correspond to on spin chains, right?
It's just it will be Z x6, for example, combinations of Z square and X square. Or D square on Z, but that's a different sector. Yeah.
If I have a finite spin chain,
yes,
the correspondence is to a truncated series, and the coupling constant is
no. In
it
fact,
goes
it goes,
the nearest neighbor goes with G squared.
Yeah, so you will have a kind of wrapping of the interaction, infinitely number of wrappings. So yeah, that's so that's technology. This technology will give you all the dependence, and of course you have an infinite series because you have an infinite series in G. Yeah. So we can say that the question of computing the dimensions is conceptually solved through this quantum spectral curve. So what we want to do is to do something which is like quantum spectral curve, but for correlation functions. So this problem was somehow the beginning of the answer was came 10 years ago with the idea of taking this three string interaction. This you imagine that you have these bands, and in order to compute the correlation functions, you start cutting the bands into 2 hexagons. So the excitations will be distributed in all the possible ways, partitioned in all the possible ways into the hexagons. And what you have to do, at least in the case when this length of the incoming chains are infinite, is just, so this is what I call asymptotic, will be just to sum over all the possible distributions of magnons on the different sides of the hexagons. The weight of the hexagon is something that is given to you, and then you have to use some gluing factors which contain the length of the pieces of the length that are distributed between these 3 cuts of the pants. And then if you want to do to consider short lengths when you have corrections from the wrapping, you will have to start decorating here, inserting here on these cuts resolution of identities to consider all the virtual particles that can jump from one hexagon to the other. So this the composition is inspired from condensed matter, where you are you are considering some non-local form factors of an operator, which introduces some defect of curvature, because if you have to understand this hexagon as in fact as a kind of origami of a surface that has right angles, and you have to introduce in the middle defect of curvature. So this type of form factors were considered by in the context of entanglement entropy for integrable field theories by Castro-Alvaredo and Jung. So you can compare this with local form factors where you are considering a rectangle space-time surface where you introduce a local operator somewhere, and then you consider a matrix element between a state with some magnons here and a vacuum state on the other side. So you just this local form factor approach is standard in, for example, in condensed matter when you want to compute correlation functions. So here it was extended to introduce these pieces of surface. In fact, you see that what you want to do is construct topologically non-trivial surfaces by gluing these pieces of surface with each other. So the bonus when you're doing this is that also you have some transformation if you want to send your excitations from one side to another, from let's say space-like to a time-like slice of your space. You're doing it with this gamma transformation, which in fact exchanges energy and momentum. For example, for an integrable relativistic theory, 2D, you'll have this parametrization of energy and momentum, which are exchanged if you are shifting theta, this rapidity theta with I pi. So using all this data, the people were able to bootstrap these hexagon factors in terms of some dynamical scalar part and some matrix part, which is in fact defined by the essentially is related to the Weisart scattering matrix. And this includes the PSU2L and left and right degrees of freedom flavors that I was mentioning before. Okay, so with these ingredients, then you can start compute not only three-point functions, like I was saying before, but also higher point functions. So a key proposal came shortly after by Federico Mazzo and Eden and Sfonderini, who proposed, for example, for the 4-point function, you could imagine that you want to decompose the 4-point function, cut it in the middle, and do some OPE decomposition, where you fuse two operators into a third one, and so cut in the middle and then cut in the two pans. But that's not the most efficient way to do it. The most efficient way to do it is to just start to cut. You imagine that this surface is topologically equivalent to a sphere with 4 insertion points, which you cut a little bit of a circle from 4 circles from a sphere, and you get this surface here. And then you start to cut it further into hexagons. So you have, for the 4-point function, you get this 4 hexagons topologically equivalent to hexagons shades. So this is reminiscent of the triangulation of the sphere with n puncture. So it's somehow it makes sense to use this kind of decomposition in order to compute a higher point function. Of course, if you want to compute your correlation function, you have to sew back hexagons along these lines. So you have to introduce your resolution of identity on each of these sides. And this is technically difficult to do. But we succeeded to do it in a simple case of an octagon. So this is what we did with Ivan and Valentina Petkova. Another technical difficulty is when you start to glue hexagons around one leg, you see that you will get some you will have some particles which will start to circulate around the leg. The procedure gives some divergences, which are the origin is understood. When you are doing this, you should recover the TBA formulation associated to a single leg. So from this procedure, we should get the information from which is encoded in the TBA and quantum spectral construction. So we know what to expect, but how to do it in practice is different. Some progress was done in this paper in 22. So that's something important to do. But to avoid getting these divergences, what people can do, what people did was consider a case when these divergences are not here, so we insert BPS operators. So you insert BPS operators, you cannot, the 3-point function of BPS operator is trivial in n equals 4 superior mirrors. So you get nothing interesting. So the first non-trivial case is the one of the 4-point function.
But just to understand the divergences, do they have a corresponding role in field theory?
So in the field, so they
because you have composite operators, so there will be divergences. But your operators are distinct; those should already be included.
Yes. So the part that comes with the it's the correction which comes with the anomalous dimension that is the divergence.
That's what's responsible for the divergences.
Yeah, exactly. Yeah. So we know what should be there, and in the language of form factors, we know that this corresponds to some divergence that we see in the diagonal form factors in infinite volume. So this is the Claire-Musardo formula. So in many ways, the origin of this divergences is understood, but we don't have a formalist to extract them systematically. I mean, to write them systematically from when you go from this form factor formalist to the TBA. Yeah. So in some sense, we made the first progress in this work. I will explain how. I'll try to be brief. So I would like to explain the configuration that goes into this simplest computation that we were able to do. So people try to engineer a 4-point function of BPS operators. So these four operators are BPS. They have large charges. They have large charges such that we have some contractions. So you have to imagine that you have contractions between this, like at weak coupling in the Bayer theory, you will have some contractions between Z and Z bar fields, X and X bar fields. So this this contraction, if they are there are many of them, they will cut off the flow of virtual particles from one hexagon to the other. So Coronado proposed a configuration that in which you effectively separate this the sphere into two octagons, if you want, two surfaces that you can see as the two hexagons that are related to each other. So the one is in the plane of the slide, and the other is on the behind. So once you do this, you can write your correlation function depending on the insertion of the points on the sphere. You have some trivial factor. Also, you have some dependence with the cross ratio of the 4 points. So via this z and z bar variable. And what is left is just a function. Once you took out the trivial dependence of the 4-point function, you are left with some dependence on the cross ratios, also of the charges of the 4 operators that I have forgotten here for a while, times the square of this octagon form factor that I will explain you how to compute in a moment. So we managed to write O as a Fredholm determinant. And this Fredholm determinant has a very rich behavior because it's, well, first it depends on the coupling constant G. Also, it depends on this cross ratio, which has also a lot of structure. So the analysis of this Fredholm determinant was performed by Belinsky and Korczewski, and there is some resurgent analysis at strong coupling that is also underway by the group of Weinok and Korczewski. So just to give a little bit of flavor of how this computation of this object called the octagon, which depends on G, Z, Z bar, and the charges of, so there are some cross ratio related to the charges of the 4 operators. So this is written as a series, a sum of all possible number of virtual particles that jump between the 2 hexagons. Also, I have considered a more general configuration where I can put here a finite number of contractions between the operators situated at 0 and infinity. So this costs nothing in terms of the computation. And then we have to compute this sum over. I make my insertion of resolution of identity here, so I have to compute the contribution of all the virtual particles that circulate between these 2 hexagons. So I have some particular kinematical factor that is not very important, and then I have an integral, multiple integral that I want to insist a little bit on, which depends on the cross ratio. So I have an integral over the rapidities, the momenta, if you want, of the individual magnons that flow here. There are also bound states, so there is a bound state index. So I have to sum over bound state index. And then the integral is constructed by some, contains one particle measure, which contains dependence on the cross ratios and on the bridge length here. And also some very robust component, which is in fact, which is a Pfaffian. It's built from some building blocks that are not extremely important, some particular dependence on the function of the rapidities through this variable here. So there is some definition of a Zhukowski transformation of this variable. It's not very important. What is important is this that this factor here, the product over the different weights can be written as a Pfaffian. So since you have a Pfaffian, an integral of a Pfaffian, you can write it as a Pfaffian of integrals. So this implies that the octagon can be written as a Fredholm Pfaffian. And the Fredholm Pfaffian can be written as a square root of a Fredholm determinant. So our octagon object here is written as a, well, there is some subtlety about some dependence on I don't want to enter into details of this. But it's a Fredholm. It's a determinant of 1 minus infinite matrix, where this semi-infinite matrix here is given by a Bessel combination of Bessel functions. So the matrix elements are given in terms of these Bessel integrals here. So the whole information about the kinematics is inside this function here, chi of t, which is expressed in, it parameterizes the dependence on the different cross ratio through some function. And in fact, you can also put the dependence on the coupling constant by shifting the integration variable making a scaling of the integration variable. You also can put the dependence on G inside this chi. So
where is the cross ratio independent?
The cross ratio, so the cross ratios, Z and Z bar are, I write it through psi and phi. So psi and phi, they are there.
Okay.
And then there is some dependence in lambda. There is some dependence of on the alpha and alpha bar. So you see that I have my Bessel kernel, which is very robust, and that only this term here changes. So this can change for this object also appears in the circular Wilson loop in computation of circular Wilson loop in the same theory with different chi. And also it appeared in a different place, a little bit unexpectedly. In the computation of the sphere partition function 2 and 3 point function in this deformation of the super-Yang-Mills theory that is the ZK on. So now, if there is no question about what I have said up to now, I will switch to the deformed theory.
Question.
Yes.
How easy is it to compute those integrals?
Sorry?
Those integrals with the Bessel functions. How
Yes.
easy is it to compute them? Are they finite or do they have problems?
No, they are. I mean, you can compute them systematically in powers of expansion powers of G.
So they converge and they don't have any problem.
Everything is, yeah. You get numbers, a lot of numbers that you can play with, and they are very fun. Yeah. So okay. So now let me say something. I mean, say a few things about the deformed theory, where this object also appeared recently. So I was telling you in n equals 4 super-Yang-Mills, there are these fields Z, Z bar, X bar, the gauge fields, and so on. So there is this quiver n equals 2 supersymmetric n equals 2 theories. They can be obtained by taking replacing n equals 4 super-Yang-Mills, the fields, by SU and C to the power k matrices. So the fields will be the gauge group is replaced by k gauge groups, and the fields are acting they are transforming with this gauge group in different ways. I don't have a lot of time to discuss the details, but essentially you can imagine that the fields of n equals 4, so they are KNC by KNC matrices, and now you have a twist. I mean, you have a twist matrix which is diagonal in this individual for these individual gauge groups, but in the big space K and C, it acts in this way. You have a root of kth root of unity, and on the diagonal you have different roots of unity of this different powers of this root of unity. So the equivalent of Z fields will be invariant with respect to this conjugation with this twist field. The same for the gauge fields, but some of the fields will be transformed by the twist. So they are acting by fundamentally with this different gauge group. So essentially, what this does on the supersymmetry is that it breaks one of these, so breaks SU4 to SU2 times SU2. You see that it breaks also the supersymmetry from 4 to 2, because there is only two copies of symmetries here left. And this theory is expected to be integrable as well, at least when the different gauge groups have the same coupling constant. So this was investigated in the year 2000 from the point of view of integrability. And also, there is a Preston-derived matrix model from using supersymmetric localization to analyze the BPS sector of this theory. And more recently, people started to compute with using this matrix model, sphere partition function, and more recently 2- and 3-point function of these twisted BPS operators that you see here. Most recently, Korczynski and Testa computed for any zk, for any k here, they computed a 3-point function of these operators. So the results, that these groups obtained from localization are the following. So I would consider this BPS vacuum sector of operators which are traces of Z to the L. These are like in n equals 4 super MUs, that I will call them untwisted. And the twisted operators are the ones where I take the product of Z fields like this, and I insert a power of the twist, alpha power of the twist, and then I take the trace. So this is the twisted sector. None of the dimension of these operators receive radiative corrections. They are still protected by supersymmetry. Nevertheless, if you compute the correlation 2-point functions of these operators, well, in the untwisted sector you get the same 2-point function as before. For the twisted sector, you get, so you can imagine that you insert some twist between two spin chains, and you contract. So this will be this is affected, in fact, by the presence of the twist, and it depends on the coupling constant. So the depends on the expression of this result is the untwisted results times or a ratio of 2 Fredholm determinants of the octagon kernel for some particular value of these cross ratios. So it's a bit surprising to see the same object appearing here. I mean, an object that we discovered studying integrability appears in supersymmetric localization. the dependence on the twist is given by this S alpha factor here, which contains the twisted sector. So you can say for the 2-point function, okay, you have to you always can normalize find an appropriate normalization where this 2-point function is computed. So the normalization of a 2-point function is a bit arbitrary. But let's look at the 3-point function. So the results for the 3-point function, first results for the 3-point function were obtained in 22. And this, as I was saying more recently by this year. So if you look at the normalized 3-point function, divide the result by normalization, again you get some dependence which is imposed by conformal symmetry. Moreover, the operator has to be extremal, which means that the length of these two operators has to be to be equal to the, so the sum of these two lengths will be equal to the third. And also there is a match of the charges, the zk charges of the three different operators. Anyway, so you have a 3-point structure constant that appears here, which factorizes surprisingly with as a product of factors associated to the three operators, and this is again given by in terms of the octagon operators. But now there is this bizarre square root here that appears in the numerator. So, okay, question for integrability people: why can we compute this from integrability? So that's what we started to do with.
Sorry, well,
yes.
I thought I would get back to the original case if I said k equals 1.
So k
Capital K equals 1.
Capital.
The 3-point function becomes trivial then.
Yeah, so then it's 1. So it will be because if k is equal 1, my alpha is should be equal to 0. I have only untwisted operators.
Oh, I see. All right.
So you see that if alpha is equal to 0, I get S alpha is equal to 0. So everything is as before. So this should be indeed trivial operators for n equals 4. The untwisted.
Sorry, I'm confused with the last statement. How did you obtain this result?
This is obtained by these two groups.
What is the method?
A student's matrix model.
Is it different from integral?
There's nothing to. It doesn't have anything to do with integrability.
Just the localization.
Yeah, it's not localization. Yeah, yeah. So you get this. You get a matrix model which is well, Gaussian part plus an infinite sum of the potential is has an infinite expansion with some zeta functions in front of that, and the zeta functions in fact are the zeta functions that you get when you compute when you're computing these integrals here, expansion in G. So in fact, it was Gregory Korczewski who noticed that there is a. I mean, the two approaches got the same object. This octagon kernel. So they Beccaria and collaborators were getting this kernel from localization, and Gregory Korczewski noticed that this was the kernel he was studying for 2 or 3 years already. So yeah, somehow this connection was made, and then these formulas for the formula for the 3-point function was not written exactly in this form, but I mean, Korczewski independently we put it in this, which is very transparent.
So when you talk about the similarity to the
Yes.
expression,
Yes.
we're talking about the Fredholm
Yeah.
determinant.
Yeah. This Fredholm determinant.
But there is no square root.
Yeah, there is no square root. So now I will try to explain quickly the square root. So you see that so now so that's our research work. So how to find the correlation function. This is not the theory that the hexagons were designed for, but we think that the structure of the n equals 4 and this n equals 2 theory are just are very similar, and there is just this insertion of the twist that makes the difference. So we take the hexagons, we take two hexagons, we insert two twists represented here by the red and blue line. We glue them by the prescription that I explained you. We sum over all the insertions of magnons on each of these sides, and okay, we get this. We get this expression. So what are the different, the origin of different expression? So first you have the magnons that live on individual cuts here, like red, blue, or green. In fact, there is nothing on the green because there is no twist. So the green, fortunately, they are not very visible on the screen. So the green magnons do not contribute because there is no twist. But the others, so the others contribute, and in fact, they give this the expression that I explained you earlier, the bridge magnon, this multiple integral that you can put in that takes the expression of a Pfaffian and so on. Then there are other, the square root, it comes from a different place. The square root comes from contact terms between pairs of magnon that leads onto different cuts. And this is this type of contact terms are those responsible for the divergences that I was mentioning earlier. But here there are no divergences, there are only finite terms. Nevertheless, this wrapping contribution are here. So this wrapping contribution gives the square root here. And there is another bizarre beast, which is a term where you have a contact term between the three types of magnons. And if you compute them, they look exactly like a bridge contribution, but there is no bridge with this length p here. So you see, you have L, K, and P is equal K plus L. So there is no bridge of length P to obtain a bridge-like contribution from that. So this determinant comes from this bridge-like contribution. So yeah, so we are happy that we obtained. I mean, there is a technical part on how to compute things. So the idea is to glue. There are square roots, so it's not really too easy to compute square roots. So we took the object, took the square of the object we wanted to compute. So this is like gluing two pens into this two torus, and then cut it differently, and then you cut it into hexagons and so on. I will spare you the details, but it was fun to do it. And when we are doing this, we are able to identify the wrapping contribution as an infinite sum of integrals, multiple integrals, which look very much like the bridge magnon contribution, but but the weight here is a little bit more complicated to exploit. There's an expression in terms of the Weisart scattering matrix. So somehow this is our most important result, that we are able to write this wrapping in a simple way. And then it's not easy to evaluate these super traces, because these matrices can be very, very large. But we are able to check up to 3 magnons, that this gave the nice expression that we have here. Okay, so I think I took a lot of your time with this story. So we were able to show that the correlation functions that you obtain by localization, you can also obtain by integrability. Well, there is probably possibility to check some conjectures about the case when you define the 2 gauge group, the coupling constant for the 2 gauge groups, to check if there is still integrability. Yeah, and we hope to be able to use this technology for this analyzing this wrapping corrections in a more systematic way. And also we hope to be able to apply similar techniques to higher point function, where there are more technical difficulties, but at least at strong coupling, there are things that there are structures that are starting to emerge. So, okay, thank you very much.
Thank you to the organizers for having me. And I'm Alessandro. I'm a PhD student of Harold in Vienna, and I will be talking about recent work with Harold and with Tung Tran on cosmological quantum spacetimes in the context of IKKT matrix model. Okay, does it work? Okay. So as a take-home message, I would like to leave that these objects that we call covariant cosmological quantum spacetimes are good backgrounds with suitable definition of good for the IKKT matrix model. They have rich physics, and we might have some different mechanisms for stabilizing the extra dimensions in IKKT. I will explain. Okay, as an outline, I will first introduce these covariant cosmological quantum spacetimes in the framework of quantum geometry that Harold talked about this morning, and including ongoing generalizations that we're working on. And then I will consider these in the context of IKKT and studying the one-loop physics around these backgrounds. So the setting, I'll go quickly because Harold already talked about it a little bit, is quantum spaces. So we want to consider Hermitian matrix configurations, XA, which we want to interpret as quantized embedding coordinates for some quantum space embedded in some flat target space, borrowing some language from string theory. And so we want these coordinate matrices to be non-commuting. So then, as probably everyone here knows, then the non-commutativity tensors has the scale of non-commutativity, which is the size of the space-time quantum cells, and which is the role that H-bar plays in quantum mechanics, for example. And more formally, non-commutative geometry is then formalized through the non-commutative algebra of functions over such quantum spaces. So in principle, what we want to do is we want to have some quantization map from some classical manifold to some quantum geometry, which does all of the things that we want quantization maps to do. So preserve the identity, traces mapped into integrals, and put some brackets related to commutators. But what we really care about in our context is we want to do the opposite. We want to be able to extract from some matrix configurations these quantized embedding coordinates. We want to extract some semi-classical notion of geometry. And to do so, we define a tool, these quasi-coherent states, So given a point in flat target space, we want to localize as much as possible these matrix configurations altogether, and we do so with this displacement Hamiltonian, hx, which for each point in target space is defined as the distance between the matrix configurations and the point. So we're trying to basically diagonalize as much as possible all of these matrices altogether and localize them at some point. And they're called in this way because this is what happens, for example, for the quantum harmonic oscillators. We're trying to, with coherent states, we localize as much as possible position and momentum simultaneously in quantum phase space. And then in this way, well, the image of this, when we take expectation values with coherent states, we define some real manifolds. But interestingly, the important structure comes from an embedding into a projective complex space, n-1 complex space. And that's, well, I will not get into the details, but that's useful because that's where you get the quantum structure from. You get the coherence length, you get the non-commutativity scale, and that's what makes this geometry really quantum.
Question?
Yes.
Can you go back a second?
Yes.
Go back a second. One more. If the x's are like a fuzzy sphere, the little x's can be any value, right?
Anything in our field.
So there's no constraint on the little x's that you would want to kind of localize them somehow further.
In general, like this map will be some kind of projection. Like for the fuzzy sphere, what you can get any little, you take any little x, then when you compute this expectation value over here, you just get the points on the sphere. And I don't know if that's addressing your question.
No, because the thing is that on the fuzzy sphere you expect that the x's are special and they're almost at the fuzzy sphere size. So the x's are not just arbitrary points.
No,
I would hope that they're kind of, but the way it's described is any x in RD, so you just get
it's kind of like we start like this Hamiltonian we define it for any point in RD.
Yes.
But then basically like this localization procedure, of course, it has two components. One is the distance between the point you started from and the fuzzy sphere, and the other component, which is what the more physical thing, is the intrinsic uncertainty. But then say you can do this very explicitly. For example, if you take a point above the North Pole, if you compute this expectation value with this ground state, you will get the North Pole for any point on that axis.
I see. Okay. So you start with any x and then you produce another x.
Yeah.
So
exactly.
That's where the constraint comes from.
Yes. Exactly.
That's now I
Okay. So then, of course, not any operator acting on the Hilbert space will be some quantized function. Otherwise, quantum mechanics would be useless. And so, because like most of the operators are deep quantum or UV things, so we define those operators for which we can do this as the almost local operators. So those are the ones that are almost diagonalized by these coherent states. And this, in fact, they do not have a counterpart for all functions on the semi-classical manifolds, but just for a subset of these functions, which we call infrared functions, which are basically roughly, they are the ones with typical wavelength much larger than the non-commutativity scale or the coherence scale, to be more precise. And very important relation for the functions and operators for which this holds is that locally commutators of the matrix configuration acts as derivatives on the underlying manifolds. Okay, so standard examples are Moyal-Weil.
Yes. What is the role of the lowest eigenvalue that you define?
Yes. So this two contributions. One exactly is this difference over here with this distance between the point and basically the point that is projected with the coherent state. And this one is what says to the non-commutativity scale, this first part. The interest, like the inability to diagonalize simultaneously the matrix configuration.
Yes.
Yeah.
I don't understand. You are writing here Hamiltonian.
Yes. It's not a physical, in principle, in general, it's not a physical Hamiltonian.
Regardless, but
Yeah.
the Hamiltonian means that there is an X and there is a P. I mean, Hamiltonian means that there is that you are going to follow some time evolution. I mean,
maybe
like H.
but maybe here then it's not a proper name to call it a Hamiltonian, but yeah, it was just it's just something acting on a Hilbert space that we minimize.
It's like the harmonic oscillator.
Okay, forget the name Hamiltonian. Call it distance operator.
Yeah, we don't have time. Yeah.
And why they are quasi-coherent states in which sense now? I mean, they are they are not exactly coherent states.
I mean, like if you take just X and P defined in Moyal-Wide plane, that's just phase space, and that is the harmonic oscillator.
So how do you build the axis for the sphere?
The standard, like
So they are coherent states.
yes, yeah.
They are not current number of coherent states.
Yes. It's just that in general, of course, given any configuration of matrices, calling it coherent is a bit of a stretch. Any other questions?
How do you define this state X? Kept under Dora notation. That's what I'm confused because you were talking about usual quantum mechanics, right? So I just wonder what is the meaning of this kept.
I mean, here we're assuming that we just like these operators, these matrix configurations are some Hermitian matrices acting on some Hilbert space, and just look for the ground states of this.
And that Hilbert space. So this Hamiltonian is n by n matrix, and you
yes.
So it's not a usual. So you're taking IKKT and you're not taking the matrix quantum mechanics. So I guess so what do you mean by Hilbert?
Yeah, this is not a physical thing. It's just something that we use to localize as much as possible the matrices. Like what are the points for the?
I can just imagine some configuration from pattern integral.
Yeah. Like these are the states from which we build, like from which we can compute traces. Basically, it's just a tool. Is it clear? Okay, where was it? So, yeah, just here a few standard examples that most people probably here know. There's the Moyal-Wille plane, which is the natural generalization of quantum mechanical phase space, in which the non-commutativity tensor is proportional to the identity on the Hilbert space. And then the fuzzy sphere is the standard example of compact quantum space, which is built from finite dimensional irreducible representations of SU2, and the generators then will be these quantized embedding coordinates. I will not go deeper into that. And so some structure that these spaces generically have, as Harold has mentioned in his talk. I will not explain how we get this, but we can extract some geometry from matrix configurations. So we can extract a metric, which is roughly an open string metric rescaled by some dilaton degree of freedom, which comes from the symplectic volume, basically. Then, as Harold explained, we can also get a frame from commutators of the matrix configuration with local coordinates, and from commutators of the background field strength, we get this object, this torsion in the Weizenburg connection, which is this weird connection that is used often in teleparallel gravity, which has zero curvature and the frame is parallel with respect to it.
One question. When you have a non-commutative parameter and you take that to zero, do you just get the ordinary commutative situation, or is there also some mathematical stuff going on?
I mean, at this level, we're just doing kinematics. So at this level, we're taking a commutative limit and we have the classical geometry. But then, of course, when we have a physical theory, in principle, we can have problems. But I will comment on then what physics we want to do with these spaces. Okay. So one class of quantized symplectic spaces that we look at, in particular, is quantized coadjoint orbits. I will not say too much about it, but in practice, what we do, like you can take for semi-simple Lie groups, the dual Lie algebra has a natural coadjoint action, and what that means is that we can construct from we can construct spaces that have a natural symmetry action, and they have a natural cosine bracket, which is given by the local the algebra structure constant, and they can be quantized basically univocally in a G covariant way, so preserving the symmetry group in terms of unitary irreducible representation of the group G. And generically, then the functions, the quantized functions, can be decomposed in a weight decomposition in terms of these group covariant harmonics. And I will show in detail what happens for the case of the covariant cosmological quantum spacetime. And at the end, also, we probe the geometry again with these coherent states, which also have a natural G action on them that relates all of them. Okay, so now let's get to the to what I want to talk about mainly, which is these covariant cosmological quantum spacetimes. They are an example of these quantized coadjoint orbits for the group SO41. It's a little tricky to get it, but we start from the SO42 algebra, SO42 algebra generators, or SU22, which has the algebra showed in the slide with the funny metric which showed negative signs. And there are specific representations for this the algebra, which I call double term representations, which remain irreducible upon reduction to SO41. So when you drop one of the negative signs, and these irreducible representations are labeled by some integer n, and I will discuss more of about the role of this n later. And in particular, there's a nice oscillator construction for these representation in terms of the fundamental spinors of SU22, and this means that in practice these matrices are very easy to build, like with a computer, because we all know how to do oscillators. Okay, and in practice, what we do to obtain these representations, we start from these SO42 representations, and we restrict the Fock space to be free of weight multiplicities, which in practice means that we restrict some number operator to be constant. And in turn, we can define some quantized embedding coordinates that are called XA there, which are built from the generators of the Lie algebra. And these, then the non-commutativity scale is set by the generators of the algebra, MAB. And these coordinates XA satisfy a Lorentzian spherical constraint, so a 4 hyperboloid constraint in R5. And that's why we call this manifold a fuzzy 4 hyperboloid. And the radius of the hyperboloid is proportional to n. And yeah, so that's why we have a hyperboloid. Of course, the joint orbit has more structure. There's not just these XAs, but we have all of the generators of the Lie algebra. And in fact, the cojoint orbit is not just a hyperboloid, but it's a CP12. It's a projective three-dimensional complex space with a funny signature, which can be seen as a sphere bundle over this 4 hyperboloid, classically. Then when we quantize this, then we have the tensor product of functions, of quantized functions on the sphere and on the hyperboloid. And in turn, this can be interpreted as higher spin modes on the hyperboloid. And as Harold argued before, we expect to get gravitons from here, so they can be interesting. But of course, we have a lot of higher spin fields that then are harder to interpret and harder to decouple. And this is the price to pay to preserve the SO13, SO14 isometry group. And yeah, any questions so far? Okay, so in practice, when we want to do physics with these with this cojoint orbit, we do some projections. So we project from the 5 XA coordinate to the first 3 plus 1, and the fifth coordinate x4 then plays the role, as I will show later, of some cosmological time scale, and in particular we call it sinh of tau, nice parameterization, which is typical of hyperboloid. Like in practice, this hyperboloid is a Euclidean ADS space, so this is the standard parameterization. And then the functions on this spacetime are generated by these x mu and by these other vectors, which we call t mu, which is also constructed from the algebra generators. And roughly they probe the internal true sphere. And they can be seen as kind of conjugate momenta to the x mu coordinate. And they also satisfy this transversal constraint t mu x mu equals 0, which is very useful for applications. And in the end, it turns out that the more interesting background to consider is this t mu vector, because it gives a nice Lorentzian metric. And another remark is that the projection that I made above is actually two-sheeted, as I'll show a picture later, but it's two-sheeted projection, and this will manifest itself as a big bounce in cosmology. Okay, what are the functions on this spacetime? As I said, they are these higher spin modes, but then now we have projected down to the first 3+1 coordinates, so we have reduced SO31 covariance for them, and the physics at the end is encoded in the fluctuations around the background. And so in particular, as Harold argued, we can interpret the spin 1 and spin 2 fluctuations as Gaussian bosons, so that we expect them to remain massless also with quantum effects. While for the higher spin modes, we don't have such mechanism. Importantly, at this level there's no local Lorentzian variance, but only the SO31 isometry group is manifest. However, we do have a very large symmetry given by the higher spin gauge symmetry, and that includes also volume preserving diffeomorphisms on the hyperboloid. I have some pictures now. So here there's a visualization, lower dimensional visualization of the projection. So in blue, there's the hyperboloid, which then we project down to 3+1 dimensions, and it's easy to the red flat hyperboloid, and it's easy to see that it's a two-sheeted projection. And yeah, and then there's another projection which instead preserves SO4 covariance, but not really useful here. And this is another thing that explains the role of X4. So we have the projected hyperboloid, and then the constant X4 slices are those hyperbolas, which then in practice are three-dimensional hyperboloids, which are then the Cauchy hypersurfaces that foliate the spacetime. Okay, now some comments about the role of the quantum number n that labels the representations. So at first we thought that only the large quantum number, this large n limit, made sense to probe the classical geometry. I mean, in the large n, it's very easy to make sense of the semi-classical geometry. It's very easy to define the coherent state via group action, and there's a nice semi-classical limit everywhere. However, we recently realized that also the minimal case with n equals 0 has a semi-classical counterpart. It's a little harder to compute the coherent states, but it can be done. The problem is that the early tau, the early X4 regime, so the early universe cannot really be probed. So we basically have a universe that is, for which the early universe is a fully quantum regime with no geometric counterpart, but then the late time behavior is practically the same as the one for large n. So in practice, at the end, when we just want to do late time physics, we just work with this minimal case because it has a simpler algebra and it's easier to do manipulations with it.
So in the large, small n limit, you obtain classical picture even at small tau.
Sorry?
Oh
yes, yes.
Picture, even at small tau.
Yes. I will show later why. Maybe I can show in, I think, next slide, in 2 slides why. Okay. So this is just a visualization for the minimal case. This represents the weights for the so for the other SO4 projection, it shows the weights for the decomposing SU2. It just shows that in the early universe, there's not enough degrees of freedom to have a meaningful geometry. But for the so this is the generic case. I'll get back to that. We can define with the metric that I introduced before that Harold talked about. We have an FLRW metric with k equals -1 spaces, and with a specific scale factor, which at late time is proportional to time, and at the early time it has this t to the 1/5 behavior. And in particular, as I mentioned, it's a big bounce in cosmology. And then from the same conjoint orbit, you can also do another projection, in fact, that has k equals 0 spacetime and a different scale factor. And we're also working on that at the moment. And so here is the relevant scales. So there's the non-commutativity scale, which is set by the square root of this x4 coordinate, this cosmological time coordinate. So in particular, the space-time coordinate scale with big R x4 and big R as is proportional to n. So for large n, there's a big separation. And then there's the cosmological curvature scale, which is much larger scale with x4 to the 3/2. So we have well separated different regimes in which we can do local physics, and that's also important.
What distinguishes k equals 0 case and k equals -1 case from the viewpoint of metrics?
I didn't show it here, but so here we're doing this very simple projection from xa to x mu, projecting to basically the flat 3+1 plane here. This flat spacetime would be something that projects kind of around here, and it turns out that the spacetime hypersurfaces are flat.
Can you get k equals 1 as well?
From this conjoint orbit, we haven't. I don't think so. But we don't have a definitive answer.
So, can you explain why you get Riemannian geometry at the end? I mean, are there just different tensors and the Riemannian is dominating, or?
I mean, that's something that eventually we should get dynamically once we have a physical theory. Of course, we have a lot of higher spin modes, including spin 2 modes. And we have arguments, qualitative arguments for why the spin 2 modes and the spin 1 modes should be the more relevant ones, but we still have to make it more precise. If that's what you're asking.
I think it goes into how stock area.
Yeah. Yeah.
How you get Riemannian geometry. That's another geometry.
What was the question about if the symplectic structure disappears?
Yeah, I mean, yeah, but I mean, the metric at the end.
Yes, a good action.
Yes. Okay. Yeah. One last thing. I think yes, about this spacetime, about the kinematics. So we're also generalizing these backgrounds. The original motivation is that these backgrounds don't solve the. So we want to solve the box T with the matrix Laplacian box T equals 0 equations, because that's the IKKT metric model equations. But these T's that I defined before solve the massive deformation of it. So we want to solve the full matrix model, and so the exact equations. And to do this, we try to do this in an SO3 covariant way. So we just add a cosmological time-dependent factor in front of this T mu. And it turns out that we notice a couple of things. This is still work in progress, so this has to be taken with a grain of salt. But generically, we see that the frame and the metric that I defined before develop higher spin components, which is weird. But these can be eliminated locally as long as the cosmological curvature scales can be neglected. So you can still do local physics. And another thing is that the solutions of these equations seem to be pathological, but maybe we'll be able to solve it with quantum effects or matter. This is not super clear at the moment. And the next step in this generalization is also considering extra dimensions and giving a dynamics to them. So adding also an SO3 covariant time dependence to them. And so this allows also to solve the equations, exact equations of motion for them. And we notice the following in particular. We notice that if we allow this kind of dependence, so we allow for, if we choose some axis of rotation in these extra dimensions, and we allow them to rotate around this axis as this cosmological time tau evolves. Well, of course, this extra dimension will develop an angular momentum that generically seems that it can stabilize the extra dimension by giving some appropriate contribution to the effective potential. But yeah, this is still ongoing work. And this is just a visualization. So basically, we just have some extra dimensions over space-time that we allow to rotate around some axis and also to shrink or evolve with their size. Okay, now what physics can we do with these spacetimes? Well, we take the physics from IKKT matrix model, which has been already talked about this morning, and I will just say a few things. So IKKT is a matrix integral in terms of this action with 10 permission matrices with Lorentzian signature and Majorana-Weil-Fermion counterparts. And it was proposed in the late 90s as a no-perturbative definition of type 2B superstring theory. And importantly, can also be obtained as a dimensional reduction to a point of 10D n equals 1 super Young-Mills, or n equals 4 super Young-Mills in 4D. And from this, you will inherit all of these nice UV properties. So we have manifest UN gauge invariance and Lorentz SO19 invariance. And importantly, we have SUSY, which is what, like generically, non-commutative field theories have very bad UV-IR mixing, which makes them hard to make sense in a commutative limit. But here, in this case, we have the supersymmetry, which tames this UV-IR mixing. And later I will show how. As a disclaimer, we just consider the weak coupling regime. So we just study the physics on the brain, the non-commutative gauge theory on the brain. We don't care about the target space physics. And at the end, we consider equations without fermionic condensate. So the equations are very simple. They're just this double commutator equals 0 equation. And non-trivial solutions of this equation will be these embedded quantum brains that I talked about at the beginning of the talk. In particular, at tree level, what we have for 4-dimensional background, if we study fluctuations around 4-dimensional backgrounds, it's quite easy to obtain n equals 4 super Young-Mills. And this is a good motivation for using 4-dimensional backgrounds for this model, because we have all of the nice UV properties of n equals 4. And at the end, so I want to talk about the one-loop physics. And well, it can be done via relatively standard methods for gauge theories, of course, in the non-commutative setting. And the one-loop effective action comes from quadratic fluctuations, and well, then taking into and summing over all of them on the quantized functions over the spacetime, and then taking into account fermions and ghosts, we can repackage them nicely into that last expression over there, which is the Schwinger parameter integral, where the alpha equals 0 limit is some UV limit, alpha equals infinity is some IR limit, and it's the integral of something that we recasted into an SO19 character, which is shown in terms of these Lorentz generators in the vector fermion representations, and this quantity, this object, delta FAB, is the commutator of the background field strength. Yeah, and I will show how we estimate this. So the traces that we still have to compute are the one over the representations of SO19, and then the one over the fluctuations, the functions on the quantized space. And at the end, we want to do for the physics. Well, for one reason is the nice UV properties, of n=4 super young males. And the other reason is, well, physical grounds. We live in a 4-dimensional world. And so we consider backgrounds with a 4-dimensional spacetime, M4, and some fuzzy extra dimension, which we call K. So the fluctuations that we have will be in the tensor product of the quantized functions over these two spaces. And so that character that I defined before can be decomposed. We can decompose the representation into 4-dimensional Lorentz representations and SO6 representations. And in particular, what we do is we expand in the Schwinger parameter the 4-dimensional part, and we get these, well, 3 contributions. The first term will contribute, just depends only on the extra dimensions, and will contribute to the one loop effective potential for it. Then the second term is the one that Harold talked about, and it's the one that contains the Einstein-Hilbert action. And in particular, we see that this delta F squared term is the one that contains the Ricci scalar, and this G6 is just a 6-dimensional character that determines the Newton constant. Then the higher order terms are higher curvature terms. And yeah. Okay. So one more thing is, on these covariant cosmological quantum spacetimes, we can study the one loop effective potential, and we have 2 main contributions. Well, we have the 3-level part, which is just the Yang-Mills action for the extra dimensions, and we make some very rough estimates using the string modes that Harold talked about earlier, and we argue that that term scales with the Kaluza-Klein scale to the 4th, with the basically typical scale to the 4th. And then the dominant part from the well contribution comes from the internal true sphere in our cosmological spacetime and its interactions to the extra dimensions. And also this we estimate in the same way. And interestingly, for dimension 2 and 4, for the extra dimensions, we get a negative contribution, which has a term proportional to mk squared. So we see that we obtain a Mexican hat kind of potential, and that means that we managed to obtain some minimum for the Kaluza-Klein scale. So it seems like we have a dynamical way to stabilize these extra dimensions, which is kind of cool considering we started from n=4, a theory that is kind of like n=4 super young males.
What are exactly the extra dimension? Is the internal sphere part of the extra?
No. It's a generic background of extra dimension at this stage. These are rough estimates that just look at the overall scaling behavior of generic extra dimensions, not the internal sphere.
You have considered split of 4 plus 6, and then here you are considering M31 crossed with S2. I mean,
it's just that so I have this T mu, the background T mu is just 4 matrices, but they are 4 matrices that are probing a 6-dimensional coadjoint orbit. So in some sense, they see the internal true sphere. They don't just see the 4 manifold.
So what happens if the dimension of K is 6?
And we cannot say anything generically. Like generically, so for 2 and 4, for a generic extra dimensional space, the contribution is negative. For dimension 6 is it depends on the space. So this could happen for specific spaces, but it's not a generic thing.
Can you compare this with CP3? I mean, is M31 as soon as like Lorentzian CP3?
Yeah, exactly. Okay, so now let's talk about the problems of all the things that I just said, at least some of them. One of them is that, as I mentioned before, this background doesn't solve the IKKT equations, but a massive deformation of it. So SUSY supersymmetry is explicitly broken. Then another problem is that on this background, the higher spin modes have negative masses, which is not good. And also this effective potential that I showed here, this minimum that I showed, I lied actually. There's this minimum actually disappears at late times. It's only an early time thing. At late times, this minimum goes to 0, so the extra dimensions disappear. This is not a stable background. And so, well, we had a funny picture for it. So we started from these, from n equals 4 super Young-Mills, which is a super conformal, no scale theory, which we picture as a spherical cow. Then we have an induced scale at early time that we picture as a real world physical cow with fuzzy extra dimensions. And then at late times, this goes away and it goes back to this idealized cow, which is spherical. However, these problems, well, this is work in progress. All of these problems seem to be addressed by these deformed backgrounds with extra cosmological time dependence. And like all three of these problems, well, the first one I already talked about. Okay. One last thing about the one loop physics. So we have, I mentioned before that we expand in alpha in the Schwinger parameter the 4-dimensional part of the of this 10-dimensional character. And well, one observation is that the expansion starts at alpha to the 4th, so all of the most UV terms cancel. Then all of the terms here, which are the higher curvature terms, well, you can integrate them, and they are all finite and subleading in the semiclassical limit. Well, not all of them, all except one. There's one term which is kind of an R square term, a curvature square term in the action, which is a little more subtle. We have arguments for why it's still regulated by non-commutativity scale, but we still have to make it more precise. Okay, so summarizing, I talked about quantum geometry and why it's a natural playground to study IKKT matrix model and to address problems of quantum gravity. Then in this context, I introduced covariant cosmological quantum spacetimes, and we showed that they have a very rich structure and potentially very rich physics. And then when you consider them as a background for IKKT, it seems like there are solutions with stable rotating extra dimensions. And then, well, at 3 level, we have gauge theories. At 1 loop, as Harold talked about, we have something that extends Einstein gravity. And potentially, it looks like we also have an effective potential that might stabilize the extra dimensions. But a lot of work has to be done to understand all of these things. Yeah, thank you.
If I come to the axioms, otherwise this will be a topic for coffee. But 2 preliminary remarks. Firstly, what I like about this place here is there is no impenetrable wall between science and literature. On some other occasions, we went out to Hamilton's observatory and heard some scientists reciting poetry. I don't know any other city in the world where that might happen. The second remark, I know next to nothing about quantum gravity. What I know is that matrix model, that's basically quantum mechanics, and ADS CFT is basically a quantum field theory. So you should think about my talk as a transition between something which makes good sense, what you have heard before, and then there's some potential wall, and there's something which makes good sense, a very different sense, starting after my talk. And what I will do is a very uncertain transition between them. So today, you might know it's an anniversary of an anniversary. So the original date, the original Bloomsday in 1904. Then there was 50 years anniversary, which Wikipedia calls a day-long pilgrimage along the Ulysses route. And certain things happened in between. In particular, in 1922, a book was written Ulysses, and we have the 100 years anniversary of 1925, where quantum mechanics was invented, and actually, as far as I'm concerned, quantum field theory was invented. Quantum field theory usually is dated to 1927. And it's true that in the first Heisenberg paper on quantum mechanics, you have no trace of quantum field theory. But in the second paper by Born and Jordan, same year, you already have quantum field theory. And so, well, the obvious names, let me write them down. And then here, Schrödinger. And it's another justification for my talk. One should not lose contact to one's origins, and I'm certainly the only one in the room here who still knew Heisenberg personally. And then, well, here, Kavanagh, which those you know don't know the place very well. You can see him a few steps from here, and you absolutely should see him. And then I looked into the Wikipedia in Heisenberg, and then I saw that 1943 it was an assassination plan. He was invited to give a talk in Switzerland, and some people planned his assassination. If he would know enough about nuclear physics, which fortunately he didn't. I will say more about that. And then, very sadly, when I heard about the 9 nuclear physicists assassinated a few days ago, then I remembered the assassination of someone who knew much more about quantum field theory. He worked on quantum geometry, inflation, quantum gravity. He would have been a better person to give the talk. It was a motorcycle bomb in Tehran. And I'll say a few things about assassinations. So, well, I initially thought that it would be easy to give a talk like that, which mixes the two things, because finally Joyce invented quarks, but that was in another book. So it's, and actually in Ulysses, you have a figure. Well, Ulysses is something which in a way gets very real. So the persons, when you look at them, then they seem to be real persons, which for me is a problem. It means I never will fully read the book, because Bloom is very voyeuristic, and because it's so a real person, when I then read these things, then I feel I should look away. But of course, then you miss the real point. But it slows me down. So I very much prefer the Dubliners, which is a great collection of stories where Joyce writes about quite sensitive things, but they're all hushed up in a way. So the first story is about the sexual abuse of boys by Catholic priests, and of course, everything is just barely hinted at. Also, the Dubliners are more political. There's one story about Parnell and all that, which Joyce had from his father. Ulysses is not completely apolitical, but there is one figure which is not even named. It's just called the citizen who talks politics. So it's in a way, it's a strange book. But, well, when I looked in Wikipedia, I leave out a few words. On the 50th anniversary of the event in the novel, Wednesday in 1954, John Ryan and Brian O'Nolan organized what was the day-long pilgrimage along the Ulysses Road. They were joined by Patrick Kavanagh, Anthony Cronin, Tom Joyce, and A.J. Leventhal, lecturer in French at Trinity College, Dublin. And I feel a bit ashamed that nobody from DIAS participated, and I want to just stress Leventhal, whom I will not mention again, in order to say something positive about Trinity College. Now, the link between the novel and the Institute, well, of course, 1922, it was a generation before the foundation of the Institute. But Joyce actually talks about one person. I said, in a way, the book is very real. And one of the things is that you never quite know the persons he writes about, the incidents he writes about. Some of them happened in real life, more or less like in the book. And one of the person who is insignificant enough to be named by his real name is Dr. Best. And Dr. Best later got a position here in Celtic Studies. And Brian O'Nolan, actually another name, Mike Megopoli, wrote, "My song is concerning three sons of great learning, Binji and Bergin and Best, ... They rose in their night shift to write for the Zeitschrift," and so on. But it was not the Zeitschrift for physics, of course, but Zeitschrift for Celtic Studies. And I won't tell you how the thing ends, because it was a little scandal in Celtic Studies and so on. Let's forget about that. But he published that in the Irish Times. And that was in spring of 1942. In the November 1942, he wrote a bit more about the Institute, and Denjo knows that I particularly like that story, so let me cite it. "Talking of this notorious Institute, Lord, what I would give for a chair in it with me 1,000 good-looking pounds a year for doing work that most people regard as recreation. A friend has drawn my attention to Professor O'Reilly's recent address on Palladius and Patrick. Understand also that Professor Schrödinger has been proving lately that you cannot establish a first cause. The first fruit of the Institute, therefore, has been an effort to show that there are two St. Patricks and no God. The propagation of heresy and unbelief has nothing to do with polite learning, and unless we are careful, this Institute of ours will make us the laughingstock of the world." Well, there followed the legal process of the century of the Institute against the Irish Times. The Institute won, and got damage of 1 pound. And Schrödinger declared that he didn't feel offended. But, well, it was talked about at the time. The whole thing was based on a lecture by Schrödinger at TCD Metaphysical Society, with arguments for not regarding causality as an irremissible necessity of thought, and claiming that open-mindedness towards these questions was the most imperative demand, which might be a hint for quantum gravity, might not. I mean, causality in quantum gravity is something quite dubious in a way. Now, so I really regard it as a shame and epitome of cancel culture that Trinity cancelled Schrödinger's name. So the Schrödinger lecture hall was renamed as Physics Lecture Hall. I hope they will change that again. The whole thing was caused not by facts, but by post-facts of Trumpian kind or so. And Walter Moore's lousy biography by a chemist who did not learn German. He was the inventor of Schrödinger's Lolita complex, which led to the whole thing. Fortunately, there are people at Trinity like Luke O'Neill who were not affected by that grace. And now people have looked, some people have looked at the original documents and found there was nothing in it to justify this cancellation. Well, that's about all I want to say about Schrödinger, because I think that Heisenberg's paper, in a way, reading Heisenberg's paper again, might be more helpful when you want to have the big picture and think about quantum gravity. I never really understood how quantum mechanics was invented. Einstein's struggle with general relativity, you can follow over the years his basic idea at the beginning, which was absolutely right, but not so easy to transform into mathematics. Then the intervention of Hilbert, which in the end led to the Einstein-Hilbert action and all that. So that's sort of easy to understand. But quantum mechanics really happened incredibly rapidly. You had what was going on before with the Bohr model and so on, which then suddenly was thrown out and forgotten. And instead you had a fully fledged quantum mechanics like Pegasus coming out in an adult form. And I noticed when I looked at it again that one really should look at Heisenberg's initial paper and the Born-Jordan paper at the same time. Otherwise, it's essentially impossible to understand what's going on. And the three people already talked about that before Heisenberg published his paper. And afterwards, they wrote the so-called Drei-Männer-Papier, the three of them together. So, and then finally, I understood Alain Kohn. Alain Kohn said quantum mechanics is a triviality. When you look at the pictures which the physicists made, they always make diagrams like that. When you have one state is decaying or being excited by a photon going to another state. So, okay, that's a bit physics notation. A mathematician only would have a vertex for one state, and then you have arrows between them, and that gives you a groupoid, and that's something which is obvious going back to the 19th century. And well, when you have an abelian group, then of course you have an abelian group algebra. But when you have a groupoid, then everything is non-commutative, so quantum mechanics is trivial. I have the feeling that this misses all the physics, but when I looked at Heisenberg's paper, it's actually what Heisenberg did, and essentially at the beginning, the only thing he wrote up. So Alec was exactly right in a way which I could not have believed before. Of course, there's one thing more that you have that the energy of the transition, or at that time frequency, when you go from a state n k, then omega nk, which is then the difference between the energies. But that's not such a big deal mathematically. But the physics in Heisenberg's first paper is very fuzzy in a way. So in order to really understand what he wanted to say, you have to look at Born and Jordan. Basically, Heisenberg seems to have forgotten the pointing vector when he develops the whole thing. So he has some electron moving around in a periodic orbit in some potential, and then classically it radiates, and the amount of energy per time is completely classical. I don't write down the factors because it's a number of 3 or so on. It's hard to remember, and I also leave out the velocity of light, but of course it's proportional to electric charge squared. And then it's the acceleration squared, just comes from the pointing vector. And then what one could say is the probability for a transition then in quantum mechanics per time. The only thing you do is you divide by the energy per transition, so by this omega. So when you have here the second derivative, then this gives you an omega squared. And so then Heisenberg says, okay, that's really you go between 2 states. So you should write that as an object with 2 indices. And then when you divide by the energy, you take out 1 factor of omega nk. And so that gives you then a 3rd power. And basically he says that you replace the unobservable position with something which makes sense and is a transition probability. Or really that is what Heisenberg should have said with these formulas. He says it in sort of fuzzy words, but then Born and Jordan write it down in a perfectly clear way. So the only way the old Greek quantum mechanics comes in is with a condition that PDQ is a multiple of Planck's constant. And that Heisenberg uses to get the commutator between Q and P, which the formula is not yet in his original paper. That's also in Born and Jordan. But when Heisenberg calculates, of course, he needs that in some sense. And he gets it from there by taking differences of n. N plus 1 minus n gives 1. So he has the scale given by Planck's constant. But the original idea to replace an observable x by an object with two indices, that is there from the very beginning without further explanation, except for the fact that the physics phenomenology tells you that that is what you should do. So there's no further physics behind, nothing Bohr atom and whatever. The only Bohr atom like stuff comes here at the second stage. At the beginning, of course, he should say, I have to make sense of acceleration squared, because that's what the Poynting vector tells you. What he says, I have to make sense of x squared, which is not really true, but of course, when he says that I have x and k, then when you have multiplication, you need to do things like that. And he did not know matrices of the time. That's of course well known. And Born and Jordan, a few months later, or a few weeks later, I don't know, pointed out that this is well known in mathematics and called matrix multiplication. But actually, they also state that mathematics is not really developed enough to give a good basis for quantum mechanics, because the matrices, the infinite matrices studied in mathematics, they were all trace class. And so when you take a trace of a commutator, then you should get 0. Trace AB is trace BA. And so you can't make sense of this relation. So in fact, the whole thing was clarified only by Hilbert, with the Hilbert space in the end. Well, that was the culmination. But what Heisenberg could do in the first paper is to use this thing here for perturbation theory. And that's, of course, the way quantum field theory was developed. You first look at the free theory, which Born and Jordan already did in 1925. And then you do perturbation expansion.
Is there a story as to why Born and Jordan didn't get a Nobel Prize?
Well, Born eventually got a Nobel Prize at a very advanced age, where he said he doesn't feel anything about it, he's too old. I don't know. I mean, certainly that was talked about earlier. Jordan was perhaps too close to the Nazis, but Heisenberg himself was very right-wing. So I don't quite well, maybe the internal documents are published by now, but I really don't know. Well, Heisenberg, of course, had other ideas, but among his sins were that he, though Alain Kohn would say, well, what Heisenberg did in the beginning was obviously deep mathematics. He talked about the groupoid algebra, which is a good mathematical concept, but Heisenberg didn't quite see it in this mathematical way. And he always was deeply skeptical about mathematics. I mean, at the beginning I thought maybe one should make a connection between Bloom of Bloom's day and Schrödinger, because there are surprising parallels when you look a bit closer. Bloom is deeply sad because he doesn't have an heir. His son died after 11 days after the birth. And Schrödinger also was deeply sad about not having an heir. He had 3 daughters from 3 different women. One of them I met here in Dublin, very nice lady. But he always wanted a son. And so on one occasion, he took a young aspiring physicist in his house and treated him with extraordinary kindness. And when you look at Ulysses and you have Bloom picking up Stephen Dedalus, it's exactly the same kind of relationship. Maybe we will hear about it a bit more in half an hour or so. But Heisenberg basically threw away his heirs. People were flocking about him. Everyone wanted to learn from Heisenberg. But at that time, he was completely hooked to his world formula, hoping that one equation would describe the whole world of physics, so the Lagrangians for fermion. And of course, some gamma matrices in between. I don't want to write down the images, just 0. So and then when I was introduced to Heisenberg, you should not think about the American context. I mean, I read in the Schwinger biography that one day a young Feynman came to Schwinger, who had never seen him before, and said, "Congratulations, Professor, you got it right." According to who had a biography of Schwinger, they both had made exactly the same mistake in a one-loop calculation. But Schwinger never forgave him, of course. I mean, when one of his Schwinger students drew a Feynman diagram, and they insisted in doing it because it was absolutely necessary, Schwinger always took his distance. So imagine rather a shy German student saying, "Professor Heisenberg, you have this well-known world formula which describes all of physics. Now you have one constant in here, which is about a Fermi." So, but when you go to gravity, you have the Planck scale, which is 20 orders of magnitude away. How do you get this 10 to the 20? And Heisenberg just lied. He said, Turing just has written a paper where he proved that gravity comes out of the equations. What Turing had done was to write a paper that if you have a mass spin 2 particle, then the only sensible interaction leads to Einstein gravity. But of course, Turing didn't say a word about the order of magnitude. Of course, Heisenberg might have said, well, if you have a high exponent, then obviously in some state you need a logarithm. And in renormalizable theories, there are logarithms. They have the wrong sign. So I don't know when Szymanczyk started to think about getting the right sign, probably not at this early stage. But the problem with Lehmann, Szymanczyk, and Zimmermann was that they were too mathematical. And Heisenberg didn't like that. They clearly were his best students, and he did nothing to them. So Lehmann told me that maybe the biggest disappointment of his life was when leaving Heisenberg, actually the three of them had some success in the United States, and in particular Lehmann. And then Lehmann came back to Germany and saw Heisenberg, and Heisenberg only said one sentence: "Na, Mr. Lehmann, wie geht's der Mathematik? How's mathematics?" So we didn't accept him as a physicist at all. But of course, maybe this fundamental insincerity, which might need really good writer to describe it, was good for the world, because I think Heisenberg was able to convince himself that he worked full-blown for the Nazi regime, and in some part of his brain, this probably was not true. I mean, Heisenberg just was too good physicist to make a 3 order of magnitude fault in the calculation of the critical mass for a nuclear bomb. He should have gotten out something like a kilogram, and he got out a ton, and then the military people said that that's too much, we can't use that. And in the Copenhagen play also, what people argue that maybe Heisenberg did that on purpose, but that's not true. After the war, they were put in farm hall, and you have the discussion, and Heisenberg really felt deeply ashamed because of the mistake which he had made. So the Americans were able to do it, and we not. We should be all ashamed and things like that. So it's an interesting thing which was going on, which really would need a good writer to fully explore. And of course, Heisenberg should have been able to construct a nuclear bomb. And the Americans had decided that if that was true, then he should be assassinated. The documents have turned up in Switzerland. At that time, that was not yet the CIA. That was called the OSS, Office of State Security, Office of Strategic Services. And they sent a baseball player by the name of Mo Berg with a weapon. But apparently, there was someone there, I don't know if American or Swiss, who had the competence to tell Mo Berg if Heisenberg would pose a danger for the world or not. And then it was decided that no, Mo Berg should not shoot. And I think the world has changed. I mean, we have seen some things which I had not expected to see in all my life. A medical person being tortured to death and the world looking and not reacting, hospitals being bombarded, journalists being killed. And everyone accepts that at a democracy. It's just, and I'm sure that they have not studied in detail the attitudes or the work of the 9 nuclear physicists which they assassinated. And certainly they did not look at Masoud Mohammadi. He had 53 papers of the kind we write. So inflation, quantum gravity, and all that. He definitely was not a nuclear physicist. And none of my Irani friends could really understand why they assassinated him. There was a long discussion in Tehran if maybe that might have been the mullahs, but it made very little sense. The major result of the assassination was that the sympathy for Israel, which existed among many Iranian scientists, was completely abolished. Before, well, they looked at the Bible and they were rather flattered the role you see in the Bible. Iran plays and the 2 old civilizations which had interesting contacts and all that. But I'm quite sure that the assassination, which was particularly, but probably meant just to terrorize the young physicists in Iran, had exactly the opposite effect. And now it's too late. And killing 9 people is of no use. There are too many. And so anyhow, I wondered when you walk around here in the building and you see the old pictures, Tong Huanwu, the Chinese guy you see in the background, he got a very high medal in China for 2 bombs and 1 satellite. So he clearly was a very intelligent person who had the capability to start the nuclear program in China. Could he have been assassinated? It's just unconceivable that would be the logic of today. In this case, you might know the story. He actually didn't want to return to China. He was linked to Cécile Moret, wanted to marry her, and she told him that she only would marry a Frenchman. So he was extremely disappointed and went back to China. So without that, probably Chinese nuclear developments would have been 10 years or so. Okay, I should say a little bit about real physics. First is what Heisenberg did and Born and Jordan, and where much of the quantum field theory came from, is to look at an atom where the force, of course, is electromagnetic. So, first question: has anyone studied the problem for a gravitational atom? Just a particle moving around a center under the influence of gravity. Of course, there might be a black hole in the middle, which would make it more difficult, and maybe you would find non-emission behavior or whatever. So that might be an interesting study if it has not been done. Then maybe somebody can help me. I heard a talk here, maybe rather in the third floor, but my memory has gotten very bad, and I don't remember who gave the talk on matrix model stuff. The one thing which you can do with Heisenberg's approach, which is not so obvious with Schrödinger's approach, at least Schrödinger did not hit upon it, but Born and Jordan got very close to it, or essentially did it, that well, just for the one-dimensional oscillator to be simple, you can look at quantities which by construction are positive definite. And you write it in terms of the energy. And then you get there might be a shift in that. Of course, it's so simple because the system is integrated. The first equation, when you have n equal 1, then well, that should be maybe 2n minus 1, 2n minus 8. No, it's not really right. Then you get energy 1/2. I don't write down the omega. And here, when you have e to the minus 3/2, greater equals 0, then you see that all the energies between 1/2 and 3/2 are excluded. So, well, in quantum field theory, what people did a similar thing, but when the system is not integrable, then you don't get the eigenvalues on the nose. You get some regions again, the eigenvalues that you belong to. And then when you get to higher inequalities, the regions become smaller. And as you see here in the beginning, initially the high end is completely open, but when you have more inequalities, more and more gaps appear. So I heard a talk here at the Institute where people took the quantum mechanics of the matrix model and used this idea to get a mass spectrum. But I don't know what is the present status. So if someone of you knows, please tell me. So The other question is what I said here about the 10 to the minus 20, of course, repeats when you look at the cosmological constant, which is something like 10 to the minus 122. Blunt times to the minus 2. So how do you get such a large exponent without having a logarithm? Maybe, well, all the arguments on the anthropic principle, but I certainly would find it more convincing if someplace in quantum gravity you see logarithms. And my last question, and here I remember a talk precisely which was in that room, given by Astrid Eichhorn, and ideas and collaboration with Christoph Wetterich at the time. And I would formulate it a bit differently. When you have ADS CFT, then this is something you really understand. It's a quantum field theory, and if I have a few minutes, then I will tell you my understanding of quantum field theory. So it might make complete mathematical sense. But if that is true, if it's not only perturbative, not only formal scheme, you would say in mathematics, but it's really mathematically well-defined object, then the gravity part also should be included in a mathematically completely well-defined object. May be complicated. Maybe when you have some coupling constant, and then you get -1g or -1g squared or whatever. I mean, you might have a complicated dependence on coupling constants when the coupling constants get small, but it should be mathematically completely well defined. So probably the only way to have some non-parametric fixed point. And there seem to be good experimental reasons to take that possibility serious, because the top quark mass comes out correctly. When you look at the Riemann normalization group flow, then only for a top of exactly the right order of magnitude does it make sense. So again, that's maybe someone can tell me. So let me use 3 minutes, because there might be some more questions. 3 minutes for those people who have not heard it, what my understanding of quantum field theory is. You have two categories. And one category is just manifolds with Riemannian. Well, I only can do it honestly in the Euclidean context. So maybe one question would be how to formulate it well in a Minkowski context. But in Euclidean context, everything works perfectly. So you have a category of Euclidean manifolds with, well, Riemannian metric, positive boundaries, and you have the Euclidean boundary might be empty, or when you have one component of the boundary, you may put it incoming or outgoing. So you have some kind of a joint operation when you move from one side to the other, and everything is continuous, and completely ordinary mathematical category. And on the other hand, you have, in the unitary case, Hilbert spaces, otherwise you have to work with slightly more general spaces, where you also have a joint. Well, I should say the categories are monoidal. You have an operation which, in this case, is just a disjoint union of manifolds, and in this case, it's the tensor product. And if you have a linear map of that kind, you have here a self-dual space, then you really a joint, and you push one component on the other side. And my only axiom for quantum field theory is that you have a functor. I can explain it in arbitrary detail. Someone asked me.
So can you state the axiom again? Just I missed a word or two in the axiom.
Functor. Just you have a functor which respects the property, the monoidal stuff, and the self-adjoint stuff. It's very similar to what people do in topological quantum field theory. The only point here, but this is really essential, that I work with Riemannian matrix, which gives me a lot more information, and allows to get out all the fields of the theory and whatever. And so, of course, in quantum gravity, you don't really believe in this separation between gravity and the states you have. So presumably, in some sense, two sides should be identified. But I think that some functorial description might possibly be indicated by that kind. There's a lot of things here which is quite intriguing. For example, dimensional reduction. When you have a higher dimension theory and you just take the Cartesian product with something common in the higher dimension, then you can understand the whole thing as an n-dimensional theory. Because it would have more fields than if the higher dimensions were not there. And presumably, one can show that here that the number of the set of quantum field theory in low dimension would be quite restricted. So presumably the whole thing only makes sense if you don't have interactive theories in higher dimensions, because the higher dimension theory would allow you to construct too many theories in low dimension, because the geometry here could be fixed arbitrarily. You don't have some gravity which would select one particular geometry. So of course, you might ask, there are theories in higher dimension, supersymmetric ones. What is the kind of restriction for the manifold here? And so on, the typical thing. But the nice thing here is at least one gets very close to the big theorem one would like to have, that all deformations of quantum field theories are given by fields of suitably small dimension. So certainly when I look at old conferences on quantum gravity, which they run for decades now, the progress seems to be a bit slower than with the pre-quantum theory. Of course, it might just be the case that either we miss the experiments, maybe a lot would become clearer if we know what dark matter is, or maybe we miss the computers. Perhaps a lot would change very rapidly if we had quantum computers. Like at some stage, we had a chance to work on a European quantum computer, but we didn't get money in Brussels. We only asked for 30 million. Maybe that was a mistake, but we had a detailed project. But when I look at what's going on nowadays, I'm not so sure that Europe and the world is ready for having more powerful computers. The way artificial intelligence is used nowadays in Gaza is just awful. So maybe in the end I should be happy that we didn't get it. I don't know. Well, we should have time for a few questions, maybe. No.